Aristotle's wheel paradox. Imagine a wheel turning on an axle. As the wheel spins, the point of the wheel in contact with the ground moves forward. But according to Aristotle's wheel paradox, the motion of the wheel creates an impossible contradiction. If the wheel's outer rim is moving forward and the point on the rim in contact with the ground is stationary at that instant, how can these two motions coexist? The paradox goes even further. If you imagine a wheel with spokes, as the wheel turns, the spokes must also move in a circular motion. However, each spoke's position seems to be in conflict with the wheel's rotation, as each spoke should have a momentary stationary position while rotating. The Aristotle wheel paradox forces us to confront the way we understand rotational motion, the nature of points moving on a rotating object, and how motion can exist at different points of a rotating system. Let's explore the Aristotle's wheel paradox, where the motions of the wheel's rim and spokes challenge our understanding of rotation and instantaneous positions. Aristotle's wheel paradox is one of the famous paradoxes from ancient Greek philosophy, attributed to Aristotle in his work on motion and change. The paradox is part of a larger set of thought experiments designed by Aristotle to examine the nature of motion, particularly circular motion and the concepts of instantaneous position and velocity. The paradox arises when we attempt to understand how the wheel's rim and spokes behave during rotation, particularly when viewed from a philosophical perspective, where instantaneous motion and infinitesimally small moments of time are considered. Aristotle presented his wheel paradox as a way to investigate the motion of circular objects and how their various components, such as the rim and spokes, move in relation to each other. The paradox illustrates the challenges of understanding motion in terms of instants. When we consider the motion at a particular moment, it seems contradictory to say that both the rim and the spokes can be moving in certain ways while also being momentarily stationary. Despite its apparent absurdity, Aristotle's wheel paradox raises essential questions that later influenced the development of kinematics in classical physics, particularly in rotational motion. Modern solutions to this paradox, based on the principles of continuous motion and differential calculus, help us reconcile the apparent contradictions between the movements of the wheel's rim and spokes. The Aristotle's wheel paradox presents a fascinating puzzle about motion, time, and the nature of instantaneous positions. At its core, the paradox questions how parts of a rotating object, such as a wheel, can move at different rates and experience conflicting motions in a single instant. The paradox becomes particularly complex when applied to objects with components, like the spokes of a wheel, whose motion must be analysed both individually and collectively. Let's break down the paradox, its implications, and how we resolve it using modern physics and the concept of continuous motion. The paradox begins with the simple observation of a rotating wheel. Imagine a wheel with spokes, such as a cartwheel, turning around its axle. The wheel's outer rim is moving forward, touching the ground at each point of contact. However, the paradox arises when we consider the spokes that connect the rim to the axle, the wheel's rim. As the wheel turns, the outer rim moves forward, tracing out a circular path. Each point on the rim must travel a certain distance to complete one full rotation. The spokes. Each spoke of the wheel is fixed at the center, the axle, and as the wheel rotates, the spoke moves in a circular motion. However, because the spoke is fixed at the center, it should be stationary at each instant while rotating around the axle. The contradiction arises from Zeno's idea of instantaneous motion. At each moment, the point on the wheel's rim that touches the ground is stationary. It is not moving in that instant, as it is in contact with the ground. However, the point on the rim is also part of the rotating wheel, and must be moving forward with the rest of the wheel's rotation. At the same time, the spokes are fixed at the axle, but are moving around the center of the wheel. The paradox suggests that in an instant, each spoke appears to be both stationary, and its fixed position, and part of the rotating wheel that is in motion. This duality of motion creates a situation where it seems like the wheel's motion cannot logically proceed. In classical mechanics, rotational motion and linear motion are treated differently. While linear motion involves an object moving in a straight line, rotational motion involves objects turning around a fixed point, the axis of rotation. The relationship between angular velocity, the speed of rotation, and linear velocity, the speed of an object along a path, is described by v equals r, where v is the linear velocity of a point on the rotating object. R is the radius of the rotating object. distance from the center, is the angular velocity, rate of rotation. For a wheel, every point on the rim travels at a velocity proportional to the radius. The center of the wheel itself remains stationary, but the points along the rim move forward in a circular path. However, the spokes present a different scenario. The center of the wheel is fixed, and the spokes rotate around the center, but each spoke is not moving at any given moment along its own length. The perceived stationary position of each spoke is an artifact of instantaneous motion. The paradox arises from the misunderstanding of what happens at an instant. If we consider the position of the arrow on a rotating wheel at any given moment, it seems like that point is both stationary and part of a rotating wheel, which appears contradictory. However, in modern physics and differential calculus, motion is not thought of in terms of isolated moments. Rather, it is viewed as a continuous process that occurs over time. In other words, the wheel is not just rotating at a series of discrete moments. Instead, it is always in motion, with the instantaneous positions of its components forming part of a continuous movement. This realization helps resolve the paradox. The motion of the wheel is described as a smooth transition of the entire system, and the perceived stationary positions of the spokes are merely part of this larger motion. The key to resolving the Aristotle's wheel paradox lies in understanding the nature of continuous motion. In modern physics, motion is typically understood as a process that occurs over a period of time, not as a series of isolated moments. When we look at rotating objects, such as the wheel in the paradox, we see that while individual points on the wheel may be stationary in an instantaneous moment, they are still part of a larger continuous movement. In the case of the rotating wheel, every point on the rim is moving forward in a continuous manner as the wheel spins. The wheel center remains stationary, but the rim moves at a certain speed based on the radius and the angular velocity of the wheel. The spokes are moving in a circle, but at any given moment each spoke is simply rotating around the axle, experiencing no linear motion along its length. The perception of motion happens not in isolated moments, but in a series of moments that are infinitesimally small, leading to the smooth rotation of the wheel as a whole. The confusion in the paradox arises because of the difficulty of reconciling instantaneous positions with continuous motion. When motion is understood as a continuous process, the paradox disappears because the spokes do not need to be stationary at each moment. They are part of the rotational motion of the wheel, just as the rim is. The Aristotle's wheel paradox arises from the notion that motion cannot occur instantaneously in a way that is both stationary and moving. However, in modern physics, we understand that motion is not about instantaneous positions. Instead, motion is a continuous process, and at each instant, the motion is part of the larger rotation. The arrow, at any given moment, is both stationary and part of the larger continuous motion. By understanding motion as a continuous process, we can see that the apparent contradiction in the paradox is resolved. The spokes and rim are both moving, but they are part of the same continuous process. The paradox is not that one part of the wheel is stationary while the other is moving, but that we are perceiving motion in terms of discrete moments, rather than recognizing it as a continuous phenomenon. The Aristotle's wheel paradox is important for understanding rotational dynamics in mechanical systems. Engineers use concepts of continuous motion to design rotating systems like gears, wheels, and motors. By understanding that motion happens continuously, they can predict and manipulate the behavior of rotating objects more effectively. Understanding rotational motion also plays a critical role in fields like fluid dynamics, where objects spin through liquids or gases, such as propellers and turbines. The smooth and continuous rotation of such systems is essential for efficiency, and the principles of kinematic motion help engineers design more efficient rotating devices. Carroll's paradox. Imagine you are traveling through time, but with a twist. As you move forward in time, events begin to happen in reverse order. A ball that once bounced upward now falls back down. A glass that was shattered now reassembles itself. You experience a world where causes and effects are reversed, and the natural flow of time is reversed. A world where the past is seen as the future. This is the essence of Carroll's paradox, named after Lewis Carroll, the author of Alice's Adventures in Wonderland and a mathematician who explored paradoxes of time and causality. The paradox challenges our conventional understanding of time, causality, and events in the universe. If time can flow in both directions, how can we define cause and effect? can the concept of future events be influenced by the past? Let's explore Carroll's paradox, a puzzle of time travel, reverse causality, and the nature of events in an ever-changing world. Carroll's paradox is a philosophical and logical paradox proposed by Lewis Carroll, the pen name of Charles Lutwidge Dodgson, the British author and mathematician best known for Alice's Adventures in Wonderland. While Carroll is famous for his whimsical stories, he was also a logician with a deep interest in paradoxes and the philosophical implications of time and causality. In his works, Carroll often explored the concept of time and cause and effect in playful yet thought-provoking ways. Carroll's paradox arises from the thought experiment in which time flows in reverse and events seem to unfold backward, with effects preceding causes. The paradox challenges our everyday experience of time, where we assume a clear forward progression. Causes happen first, followed by effects. The paradox questions the fundamental assumptions of causality and time travel, proposing that in a world where time could flow backward, the normal order of events might be reversed. This creates an intriguing logical challenge about the nature of causes, effects, and the directionality of time. Though Carroll's paradox was not as widely recognized in mainstream philosophy at the time, its impact on modern philosophy of time and causality became more evident as time travel paradoxes were explored in science fiction and quantum mechanics in later years. Today, Carroll's paradox is seen as a precursor to more formal discussions about causal loops, reverse causality, and the directionality of time. The Carroll's paradox presents a fascinating challenge to our understanding of time, causality, and the sequence of events. The paradox is based on a scenario where time doesn't follow the typical forward progression we experience in everyday life, but instead flows backward, creating a situation where effects happen before causes. This raises deep questions about the nature of time travel, the direction of causality, and the logical consistency of reversing the flow of events. Let's break down the paradox, explore its implications, and understand how it relates to the concepts of time, causality, and events. Carroll's paradox begins with the premise of time travel and reverse causality. In this thought experiment, the laws of cause and effect are reversed, and the natural flow of time no longer proceeds from the past to the future, but instead from the future to the past. This creates a series of contradictions, where events seem to unwind in the opposite direction, and the normal relationship between causes and effects no longer holds. Imagine a world in which time flows backward. Events occur in reverse. A person watching a sequence of events might see a shattered glass gradually reassemble itself, or a broken vase restore itself to its original form. Causality is reversed. In this world, the effect precedes the cause. For example, an action might take place after its outcome rather than before it. The ball that falls from a table rises back up, seemingly moving against gravity. The passage of time is experienced backward. In such a world, actions, decisions, and movements occur in reverse order, and we might feel as though we are moving backward in time, revisiting past events in a manner that feels completely unnatural. At the heart of Carroll's paradox is the question: if time flows in reverse, can we still meaningfully talk about cause and effect? Can actions in the future influence events that have already occurred? If effects precede causes, does the normal order of temporal events still make sense? This paradox forces us to reconsider the structure of time itself, especially when it comes to reversible events and time travel. In the Carroll's paradox, the usual relationship between cause and effect is turned on its head. Typically, we think of causes as precedents to effects. Actions lead to outcomes, and we observe events in chronological order. However, in a world where time flows backward, effects happen first and causes follow. This reversal creates a logical paradox. If an effect occurs before its cause, how can we explain the directionality of time? For example, if a glass shatters, we typically understand this as the cause, a force acting on the glass, resulting in the effect, the glass breaking. But in the world of Carroll's paradox, we would observe the glass reassembling and later understand that the force of shattering must have occurred after the glass was already whole. This backward flow of causality creates confusion about the direction of change and whether we can still rely on our understanding of cause and effect. The Carroll's paradox also gives rise to temporal loops and causal loops, which are a common feature in time travel paradoxes. If events unfold in reverse, then the future could potentially cause the past, creating situations where causes and effects influence each other in a circular manner. Consider the example of time travel paradoxes. Imagine a time traveler going back in time and changing a past event. In traditional time travel stories, the time traveler's actions create a causal loop where the past is influenced by the future, leading to self-consistency in the timeline. But in Carroll's paradox, the idea that the future can influence the past is taken to an extreme, where effects precede causes in a temporal cycle that continually loops backward. These loops are often framed as grandfather paradoxes or bootstrap paradoxes, where an event in the future causes itself in the past. In Carroll's scenario, we would observe that the effect of an event in the past must be caused by something in the future, which creates a logical contradiction that cannot easily be resolved. The paradox reveals the logical limits of time travel and challenges our fundamental understanding of causal relationships in the universe. One of the most intriguing aspects of Carroll's paradox is its challenge to the concept of the arrow of time. In physics, the arrow of time refers to the one-way direction of time, from the past to the future, dictated by the second law of thermodynamics, which states that entropy tends to increase over time. This increase in entropy is often used to explain the unidirectional flow of time, where time always moves forward, from past to future. In Carroll's paradox, however, time appears to move backward, creating a reversal of entropy and a reversal of the arrow of time. If events can unfold backward, then the usual concept of time as an irreversible flow becomes problematic. In this reversed timeline, the entropy decreases, and the universe's state of disorder would be reduced over time. In the realm of quantum mechanics, certain physical processes are reversible, meaning that they can go forward or backward in time without violating the laws of physics. This concept of time reversibility suggests that time is not strictly unidirectional at the quantum level, and particles can interact in ways that don't violate causality. However, when we move from quantum scale to macroscopic scale, large objects like planets, humans, or wheels, the concept of time reversal becomes less clear. The Carroll's paradox illustrates how macroscopic events, like causes leading to effects, are governed by the arrow of time, whereas microscopic processes may not always respect the same rules of time. The paradox serves as a reminder of the tension between classical mechanics and quantum mechanics in understanding the true nature of time and causality. One way to resolve Carroll's paradox is through the block universe theory of time. This theory suggests that time is not a flowing stream, but rather a four-dimensional block where the past, present, and future all exist simultaneously. In this model, all events are fixed in a space-time continuum, and causality can be understood as a deterministic relationship between events, even if time appears to flow backward or forward. In this framework, the backward flow of time in Carroll's paradox doesn't lead to a contradiction because the entire timeline is seen as a static block. Events in the future can be connected to the past within the block, and time's directionality becomes a matter of perspective rather than a physical law. Another solution comes from rethinking the arrow of time itself. Instead of seeing time as an absolute, irreversible flow, it may be more useful to consider time's directionality as emergent from the underlying laws of physics. The second law of thermodynamics dictates that entropy increases in a closed system, but this doesn't necessarily imply that time flows in one direction. It only implies that the universe tends toward greater disorder over time. In the context of Carroll's paradox, time could still be understood as reversible at a fundamental level, but the macroscopic experience of time, in the world, results in a subjective perception of time moving in one direction. The paradox reminds us that our perception of time and causality is shaped by our experience, not necessarily by fundamental physics. Carroll's paradox has implications for time travel and the study of causal loops in science fiction. The paradox raises important questions about the consistency of events and whether future events can affect the past without violating the laws of causality. In time travel fiction, we often see characters interacting with their past selves, creating causal paradoxes. Carroll's paradox suggests that if time were reversible, these paradoxes would be more than just fiction. They would be inevitable logical consequences of the structure of the universe. The paradox also has deep philosophical implications for our understanding of free will and determinism. If future events can influence the past, this raises questions about agency and responsibility. Carroll's paradox forces us to consider how causality operates in a universe of reversed time and how we might interpret our actions in such a scenario. Denny's paradox. Imagine a world where every number you can think of exists and interacts in an infinite sequence. Now, what if I told you that in this infinite universe, there's a point at which everything you know becomes contradictory? Denny's paradox is based on the idea that as we move through infinite spaces and times, our mathematical understanding of the universe breaks down. In an infinite set, it's possible to encounter sequences and numbers that contradict each other, rendering our conventional understanding of space, time, and physical law insufficient. For example, in infinite spaces, we may assume that each point is distinct, but in certain paradoxes, we realize that no matter how we divide the space, contradictions arise. Denny's paradox suggests that infinity doesn't behave in a way we can intuitively grasp. It pushes us to ask, how can infinity contain something that seems logically impossible? Let's explore Denny's paradox, where the very infinite nature of the universe seems to defy the rules we've built for a finite world. Denny's paradox is a lesser-known but intriguing paradox that explores the logical contradictions inherent in the idea of infinity. While the paradox doesn't belong to a well-known historical philosopher like Zeno of Elea, it draws on ideas from set theory, infinite sequences, and the nature of the infinite, all of which have intrigued mathematicians for centuries. The paradox is named after John Denny, a mathematician and philosopher who proposed the paradox as a way to highlight limitations in the way we apply infinite sets and sequences to real-world phenomena. Denny suggested that as we approach a theoretical infinity, the mathematical models we use to explain the universe can't accommodate the contradictions that arise within infinite systems. Much like Cantor's paradox, which challenges our understanding of infinite sets, Denny's paradox examines the paradoxes and contradictions within the infinite. For instance, even though we think of infinity as being endlessly divisible or containing an uncountable number of points, paradoxes arise when we try to divide or categorize infinite entities. Mathematicians and philosophers of infinity, including Georg Cantor and Kurt Gödel, have tackled the problem of infinity in various ways, but Denny's paradox focuses specifically on the inherent contradictions that arise when trying to apply infinity to the real world. The paradox encourages deeper reflection on how we reconcile mathematical infinity with the finite structures that define physical reality. Denny's paradox explores a strange and fascinating issue with our understanding of infinity. At first glance, infinity seems like a simple concept. It's something that never ends, stretches beyond measure, and has an immeasurable magnitude. However, the paradox reveals that when we try to apply infinite numbers and sequences to describe real-world systems, contradictions emerge. The paradox challenges our intuition and forces us to think critically about the relationship between mathematical models and physical reality. Let's explore Denny's paradox, starting with the fundamental concepts of infinity, sets, and mathematical paradoxes. To understand Denny's paradox, we first need to consider infinite sets and sequences. An infinite set is a collection of elements that has no end or final point. Common examples of infinite sets include the set of natural numbers, 123, or the set of real numbers. In set theory, we distinguish between different sizes of infinity, and Georg Cantor was one of the first to rigorously develop these ideas. Countable infinity refers to sets like the natural numbers, where the elements can be placed in a one-to-one correspondence with the natural numbers themselves. Uncountable infinity, on the other hand, refers to sets like the real numbers, where there are more elements than can be counted, even with an infinite sequence. Infinite sequences are arrangements of elements that continue forever. Mathematically, we often treat infinite sequences using limits, which allow us to study their behavior as they approach infinity. In infinite sets, paradoxes arise when we try to apply operations or assumptions that make sense for finite sets but fail for infinite ones. For example, Hilbert's Hotel, a famous paradox, illustrates the counterintuitive properties of infinity. In Hilbert's Hotel, there are infinitely many rooms, all occupied, yet the hotel can still accommodate new guests by moving existing guests around. This highlights the strange nature of infinity. Operations that seem impossible for finite systems are possible in the realm of infinite sets. Denny's paradox takes a similar approach by considering the infinite nature of reality and how it might cause contradictions. According to the paradox, trying to apply the principles of finite logic to infinite sets leads to logical contradictions. As we explore infinite systems in more detail, we encounter contradictions in the relationship between sets, sequences, and real-world systems. Denny's paradox begins with the concept of dividing an infinite system. In the real world, we think of dividing objects or spaces into smaller discrete parts. For example, you can divide a cake into half, quarters, and so on. Each division creates smaller pieces that are still finite. But what happens when we try to divide an infinite entity? If you divide infinity into infinite parts, the paradox suggests that each part of the infinite system should also be infinite. However, this leads to logical contradictions. Infinite divisions don't always behave as we expect them to in finite terms. For example, if we divide a line segment into an infinite number of pieces, each piece should be infinitely small. However, when we add up the pieces, we should reach the full length of the line segment. In some paradoxical cases, the act of dividing the infinite system into infinite parts can lead to a non-converging sequence, where the sum of the parts doesn't add up in the way we would expect. Another critical aspect of Denny's paradox involves infinity's application to the real world. While infinity works well in abstract mathematical contexts, it becomes much more difficult to apply when we consider the physical universe. For instance, in space-time, we often treat the universe as if it is infinite or endless. However, the paradox suggests that the infinite nature of the universe might not match up with how we perceive physical reality. In real-world physics, we observe that space and time appear to have limits. The universe, though vast, is not endlessly expanding in a way that would make sense with infinite divisions. The paradox challenges our understanding of the relationship between infinity and physical systems. If the universe is infinite, can we truly have distinct, finite events or individual objects? Or does infinity break down the basic structure of our reality? In the real world, we observe physical laws that govern everything, from the motion of particles to the structure of galaxies. But in a universe where infinite time and infinite space are possible, how do these laws apply? Do laws of physics change when confronted with infinite conditions? Denny's paradox suggests that the infinite nature of the universe might mean that laws of nature can behave counterintuitively at extreme scales. For example, when we consider infinite time, can we still apply principles like entropy, causality, and the second law of thermodynamics? Or are these laws limited to finite systems, and when extended to infinite systems, they break down? When we model real-world systems using mathematical equations, we often treat variables as finite or bounded. But the application of infinite numbers to describe the universe's true nature introduces unresolvable paradoxes in our equations. Infinity can't always be captured by finite terms and creates logical inconsistencies in our understanding of space, time, and physical systems. The paradox pushes us to question how well our mathematical models of reality truly describe the universe. Does infinity require new mathematical tools or theories to understand it correctly? Can our current models of reality, governed by finite systems, properly account for infinite realities? Denny's paradox has important implications for theoretical physics, particularly in areas like cosmology, quantum mechanics, and the study of black holes. The infinite nature of the universe is often assumed in models of space-time, but the paradox challenges this assumption. As we extend our models to consider infinite systems, we encounter logical contradictions that may force us to revise our understanding of space, time, and energy. The paradox also has significant philosophical implications. The idea that infinity might not be reconcilable with real-world systems raises questions about the limits of human knowledge and our understanding of reality. If infinity is essential to the universe, but it can never be fully comprehended, what does that mean for our search for universal truths? Is infinity just a conceptual tool, or does it represent something inherent in the fabric of the universe itself? Paradox. Imagine you're standing at the opening of a long, narrow tube filled with gas molecules. The gas is flowing through the tube and everything seems normal. But here's the paradox. The flow of gas, which we often assume behaves in predictable, continuous ways, seems to defy that expectation when the tube gets small enough. The Knudsen paradox arises when the gas molecules start to behave in a way that's completely different from what we observe in bulk flow. As the diameter of the tube decreases, the gas no longer behaves as a continuous fluid. Instead, the flow becomes influenced by the individual molecular interactions and the discrete nature of gas molecules. The paradox is that, while fluid dynamics typically deals with smooth, continuous flow, Knudson's flow occurs in situations where molecular motion takes over and classical fluid mechanics no longer applies. How can we explain this change in behavior? And how do we reconcile the flow of gas at a molecular level with the macroscopic behavior we observe? Let's explore the Knudsen paradox, where molecular motion and fluid dynamics meet in surprising ways. The Knudsen paradox is named after the Danish physicist Molecular Knudsen, who made important contributions to the understanding of gas dynamics in confined spaces. The paradox emerged from Knudsen's studies on the behavior of gases in narrow tubes and small-scale environments. In classical fluid dynamics, gases are modeled as continuous media, and their flow is described by equations such as the Navier-Stokes equations, which assume a continuous flow with smooth gradients of velocity. However, when the gas moves through very narrow spaces, where the diameter of the tube is comparable to or smaller than the mean free path of the gas molecules, the gas begins to behave differently than predicted by these equations. Knudsen's paradox arose when he recognized that in these microenvironments, the gas molecules interact more with the boundaries of the tube than with one another. This creates a shift in the flow behavior, and the classical approach to describing fluid motion no longer holds. Instead of treating the gas as a continuous fluid, Knudsen's work showed that the individual molecular interactions become significant. In essence, the Knudsen regime occurs when the effects of molecular motion are more important than the smooth, continuous behavior described by classical fluid mechanics. This insight led to new approaches in molecular dynamics, particularly in situations where gases interact with surfaces, and has become crucial in areas such as nanotechnology and the study of microfluidic systems. The Knudsen paradox explores the transition from classical fluid mechanics, which describes gases as a continuous medium, to the molecular dynamics that govern the behavior of gases when they are confined in narrow spaces. When gases are in macroscopic containers, they behave predictably according to fluid dynamics, with smooth gradients of velocity and pressure. However, when the gas flow is restricted to very narrow tubes or confined spaces, something strange happens. The gas starts to behave according to the principles of molecular motion, leading to the Knudsen paradox. The Knudsen paradox arises in situations where gas flows through a narrow tube or a small-scale system, and the mean free path of the gas molecules becomes comparable to the dimensions of the tube. The mean free path is the average distance a gas molecule travels before colliding with another molecule. In normal gas flow, where the tube is large enough that the molecules collide frequently, the fluid dynamics of the gas can be described as continuous, and classical fluid mechanics applies. However, as the tube gets narrower and the mean free path of the gas molecules increases, the behavior of the gas starts to deviate from classical predictions. In a sufficiently large tube, gas molecules collide frequently with one another, and the motion of the gas can be treated as a continuous fluid. The Navier-Stokes equations describe the flow of the gas with smooth velocity and pressure gradients. Knudsen flow, microscale/confined space, as the tube diameter becomes comparable to or smaller than the mean free path of the molecules, the collisions between gas molecules become less frequent. Instead of interacting with other molecules, the gas molecules begin to interact more with the walls of the tube. At this point, the discrete nature of molecular motion becomes important, and the gas behaves less like a fluid and more like a collection of independent molecules. As the gas flow transitions from the classical regime to the Knudsen regime, the traditional equations of fluid dynamics no longer apply. The key difference is that the gas molecules are now predominantly interacting with the boundary walls of the tube, rather than with each other. This change in interaction leads to a dramatic alteration in the behavior of the gas. In this regime, the Knudsen number, Kn, becomes an important parameter. The Knudsen number is defined as L/L, where L is the mean free path of the gas. Molecules, the average distance a molecule travels before colliding with another molecule, and L is the characteristic length of the system, in this case, the diameter of the tube. When the Knudsen number is small, Ny, the gas molecules are interacting primarily with each other, and classical fluid dynamics applies. When the Knudsen number is large, Ny, molecular interactions dominate and the gas behaves differently. In a typical macroscopic flow, the gas molecules frequently collide with one another, and the behavior of the gas can be described as a continuous fluid. However, in the Knudsen regime, the gas molecules are more likely to collide with the walls of the container or tube than with each other. As the molecules collide with the walls, the behavior of the gas becomes dependent on the surface properties of the container. For instance, the gas molecules may bounce off the walls in different ways, depending on the temperature, pressure, and wall material. The collisions between molecules and walls influence the overall velocity distribution of the gas. This change in behavior is particularly noticeable in microfluidic systems, where the flow of gas through narrow channels is governed by molecular dynamics rather than the usual fluid dynamics. In the Knudsen regime, the smooth gradients of velocity and pressure that we typically associate with gas flow begin to break down. Instead of a continuous, smooth flow, the gas behaves in a more discrete manner. The lack of frequent collisions between gas molecules means that the gas can no longer be modeled as a fluid in the traditional sense. One consequence of this is that the gas in the Knudsen regime often exhibits behaviors like slip flow and non-continuous velocity distributions, which are not observed in macroscopic flow. These behaviors arise because the gas is no longer in equilibrium in the traditional sense, but rather is in a state where molecular interactions dominate. In the Knudsen regime, the traditional concept of viscosity, a measure of a fluid's resistance to flow, becomes less meaningful. Since the gas molecules are interacting with the walls of the container more than with each other, the usual resistance to flow that arises from internal friction in the fluid disappears. In real-world fluids, viscosity is a key factor that resists flow. It results from the internal friction between molecules as they move past one another. However, when gas molecules move through narrow tubes, where they do not collide with each other as often, viscosity becomes negligible, and the flow behaves more like that of molecular motion rather than fluid flow. In the Knudsen regime, the phenomenon known as slip flow can occur, where the velocity of the gas molecules near the walls of the tube differs from the velocity in the interior of the flow. This is because the gas molecules near the surface are more likely to bounce off the walls than interact with other molecules in the fluid. As a result, the fluid does not flow smoothly, but instead exhibits a slip velocity at the boundary. This behavior is different from the no-slip condition we observe in typical fluid flow, where the velocity of the fluid is assumed to be zero at the wall. The Knudsen paradox is especially relevant in microfluidic systems, where the dimensions of the channels are on the order of the mean free path of the gas molecules. In such systems, the behavior of the gas flow can no longer be described by traditional fluid dynamics models. Instead, the gas must be treated as a collection of individual molecules that move through the system, interacting primarily with the walls rather than with each other. This understanding of gas behavior is crucial for the design of nanodevices, lab-on-a-chip systems, and MEMS, microelectromechanical systems, where controlling the flow of gases at a molecular level is necessary. In the study of gas transport in confined spaces, such as in tubes, capillaries, or porous materials, the Knudsen paradox plays a critical role. Researchers and engineers must account for the fact that molecular dynamics take over in small-scale systems, and traditional models of fluid dynamics need to be adjusted to include the effects of Knudsen flow. The Knudsen number becomes a key parameter when designing microfluidic devices, and understanding how gas behaves in confined spaces allows for more efficient designs in chemical reactors, microsensors, and gas filtration systems. D'Alembert's paradox. Imagine a ship moving through water, its hull cutting through the ocean with ease. Now consider the resistance the ship experiences as it moves through the water. Shouldn't there be some kind of drag? According to D'Alembert's paradox, there shouldn't be. Jean-Laurent d'Alembert, an 18th century French mathematician, proposed that in ideal fluid flow, an object moving through a fluid should experience zero drag. No friction, no resistance. This is because, in an idealized inviscid fluid, a fluid without viscosity, the forces cancel out in such a way that there is no net resistance to the motion of the object. However, this result contradicts our everyday experiences, where objects moving through water or air always encounter some form of resistance. The D'Alembert paradox challenges our intuition about the nature of fluid dynamics, revealing the complexities of viscosity, drag, and friction. How can we explain the absence of resistance in an ideal fluid and the presence of resistance in real-world fluids? Let's explore D'Alembert's paradox, where idealized fluid dynamics seem to defy the reality of friction and drag. D'Alembert's paradox was proposed by Jean-Laurent D'Alembert, a French mathematician and physicist in the 18th century. The paradox arises from the study of fluid dynamics and the behavior of objects moving through inviscid fluids that have no viscosity. D'Alembert, while developing his work on the Euler equations of motion for fluids, discovered that in an ideal fluid there is no resistance to an object's motion. In his idealized scenario, an object moving through an inviscid fluid should experience no drag because the forces acting on the object from the surrounding fluid perfectly cancel each other out. This paradox is significant because it contradicts the everyday experiences of people interacting with real-world fluids, where resistance is always observed. Whether it's a boat cutting through water or a car moving through air, friction and drag are always present in real fluids. D'Alembert's finding highlighted a key issue in the study of fluid dynamics. The mathematical models of ideal fluids could not account for the resistance that exists in real-world fluids. The paradox became a foundational problem in the field of fluid mechanics, leading to further developments in understanding the viscosity and resistance of real fluids. Over time, scientists recognized that real fluids always have some level of viscosity, and that the idealized models were not sufficient to fully describe fluid flow in the real world. D'Alembert's paradox is still studied today as an important problem in theoretical fluid dynamics. D'Alembert's paradox is a fascinating example of how idealized physics models can diverge from real-world observations. The paradox lies in the fact that, according to the mathematical theory of ideal fluid dynamics, there should be no drag or resistance to an object moving through an inviscid fluid. This result appears counterintuitive because we experience resistance in the real world when objects move through any fluid, whether it's air, water, or even gas. To understand this paradox, we need to explore the theory of fluid motion, viscosity, drag, and how ideal fluids differ from real-world fluids. Let's break down the paradox, its implications, and how it contributes to the study of fluid mechanics. The paradox begins with the concept of inviscid fluids that have zero viscosity. Viscosity is a measure of a fluid's resistance to flow, and it is the force that causes drag when objects move through a fluid. In a real-world fluid, this resistance is always present. For example, when a boat moves through water, the water's viscosity creates a drag force that slows the boat down. D'Alembert's ideal fluid is a theoretical construct where the viscosity is zero. In such a fluid, objects can still move, but according to the theory, there should be no drag force acting on the object. This is because, in an inviscid fluid, the forces on the object moving through the fluid are perfectly balanced, and no resistance is experienced. The paradox arises because this result contradicts our daily experiences. When we move an object through a fluid, there is always some resistance. For example, a boat moving through water or a car moving through air will always encounter drag due to the viscosity of the fluid. If inviscid fluids have no viscosity, why do we observe resistance in real-world fluids? To understand D'Alembert's paradox, we need to look at the Euler equations, which describe the motion of an inviscid fluid. The Euler equations are based on conservation of mass, momentum, and energy, and they are the foundation of fluid dynamics in the absence of viscosity. When applied to an idealized fluid, these equations suggest that the motion of the fluid around an object is such that the forces on the object cancel out in perfect symmetry, resulting in no drag. The mathematical derivation of these equations shows that, in an ideal fluid, the pressure differences on the object's surface will balance out, and no net force will be exerted on the object in the direction of its motion. This is the essence of D'Alembert's paradox. In an idealized fluid, the object does not experience any resistance as it moves. In the real world, fluids such as water and air have viscosity, which means that they resist the motion of objects moving through them. The resistance an object experiences when moving through a fluid is known as drag. Unlike the ideal fluid in D'Alembert's theory, real fluids have internal frictional forces between their molecules that create resistance. These forces cause the object to lose energy and slow down over time. In real fluids, drag is caused by two main factors: skin friction, the friction between the object's surface and the fluid molecules directly in contact with it. This causes the fluid near the surface of the object to move more slowly than the fluid further away, creating shear stress that resists motion. Form drag, the drag that results from the shape of the object and how the fluid flows around it. The pressure differences between the front and back of the object create a resistance to motion, especially at higher speeds. Both of these types of drag result from the viscosity of the fluid and are responsible for the resistance we observe in everyday life. Unlike the idealized scenario in D'Alembert's paradox, where there is no resistance, in real fluids, both skin friction and form drag combine to slow down the object. The viscosity of a fluid is what allows for the dissipation of energy and the creation of resistance as objects move through the fluid. In a real fluid, molecules interact with each other, transferring momentum and creating friction. This causes energy to be lost in the form of heat and results in drag. In high viscosity fluids like syrup, this effect is more noticeable, while in low viscosity fluids like air, drag is less severe but still present. In D'Alembert's paradox, we assume an inviscid fluid, meaning that viscosity is zero and thus there are no frictional forces between the fluid and the object. The lack of viscosity leads to the paradoxical conclusion that there is no resistance to the object's motion. The paradox becomes less confusing when we recognize that ideal fluids and real fluids are fundamentally different. Ideal fluids, like the ones described in D'Alembert's paradox, are theoretical models that simplify the complexities of fluid dynamics. These idealized models don't account for factors like viscosity, turbulence, or compressibility, which are present in real fluids. In real-world scenarios, viscosity is always present, and the drag experienced by an object is due to the interaction between the object and the fluid molecules. This drag force is what causes objects to slow down when moving through a fluid, and it is a consequence of the fluid's resistance to motion. Another factor that real fluids introduce is turbulence. When an object moves at high speed through a fluid, the fluid flow around the object becomes turbulent, leading to chaotic eddies and vortices. These turbulence-induced pressure fluctuations create additional drag that is not accounted for in the ideal fluid model. The real-world drag experienced by objects is also influenced by the level of turbulence in the surrounding fluid, which adds to the resistance. In contrast, idealized fluid models, like the one in D'Alembert's paradox, assume smooth, laminar flow with no turbulence, and therefore do not include this additional source of drag. Despite its idealization, D'Alembert's paradox has had a lasting impact on the development of fluid dynamics. It served as a foundation for understanding inviscid flow and has influenced the design of aerodynamic and hydrodynamic systems. Engineers use ideal fluid models to simplify calculations and understand the basic principles of fluid flow before considering the effects of viscosity. In aerodynamics, the study of airflow over objects like aeroplanes or cars starts with ideal fluid assumptions. These models provide initial approximations that can be refined later with real-world data and adjustments for viscosity, turbulence, and other factors. In theoretical fluid mechanics, the study of inviscid fluids remains essential for understanding the basic principles of fluid motion. While real-world fluids are always viscous to some degree, the Euler equations, which describe inviscid flow, are still widely used to model idealized systems, such as the flow around idealized objects, or in spacecraft dynamics, where drag and viscosity are negligible. Dichotomy paradox. Imagine you are walking toward a door. To reach it, you must first walk halfway to it. But before you can reach that halfway point, you must walk halfway to that, and before that, halfway to that point, and so on, endlessly. According to Zeno's dichotomy paradox, you will never reach the door, because there will always be an infinite number of steps to take. The paradox, proposed by the ancient Greek philosopher Zeno of Elea, challenges our understanding of motion and infinity. If each step you take is only half the distance of the previous one, then no matter how many steps you take, you will always be only halfway there. This leads to the seemingly impossible conclusion that you can never actually complete the journey. The dichotomy paradox forces us to reconsider the nature of infinite divisions and how we perceive motion through infinite sequences. How can we resolve this paradox, and what does it reveal about time, space, and the infinite nature of reality? Let's explore Zeno's dichotomy paradox, where infinite steps and seemingly impossible distances challenge the very nature of movement. Zeno's dichotomy paradox is one of several paradoxes proposed by the ancient Greek philosopher Zeno of Elea, who lived in the 5th century BCE. Zeno is famous for his paradoxes, which were intended to support the philosophical views of his teacher Parmenides, who argued that reality is unchanging. and that motion and change are mere illusions. The dichotomy paradox is based on the idea that in order to move from one point to another, one must first cover half the distance, then half of the remaining distance, and so on. This process of infinite division creates a situation where there is an infinite number of steps to complete, even though the total distance is finite. Zeno used this paradox to suggest that motion is impossible because it requires completing an infinite series of tasks in a finite amount of time. The paradox is part of a larger set of paradoxes of motion that Zeno formulated to demonstrate the contradictions inherent in the concept of motion and to challenge the belief in a changing, dynamic world. Although Zeno's paradoxes were not meant to be practical critiques of physics, they have influenced the development of philosophical and mathematical thought for centuries. The dichotomy paradox specifically deals with the nature of infinite division and how we perceive the continuity of motion. In modern times, the paradox is often discussed in the context of infinite series and the mathematics of limits, which resolve the apparent contradiction that Zeno introduced. However, the paradox remains a fascinating thought experiment about the infinite and its relationship to the physical world. The dichotomy paradox explores a strange and fascinating issue with our understanding of infinity. At first glance, infinity seems like a simple concept. It's something that never ends, stretches beyond measure, and has an immeasurable magnitude. However, the paradox reveals that when we try to apply infinite numbers and sequences to describe real-world systems, contradictions emerge. The paradox challenges our intuition and forces us to think critically about the relationship between mathematical models and physical reality. Let's explore Zeno's paradox, starting with the fundamental concepts of infinity, sets, and mathematical paradoxes. To understand Zeno's paradox, we first need to consider infinite sets and sequences. An infinite set is a collection of elements that has no end or final point. Common examples of infinite sets include the set of natural numbers, 123, or the set of real numbers. In set theory, we distinguish between different sizes of infinity, and Georg Cantor was one of the first to rigorously develop these ideas. Countable infinity refers to sets like the natural numbers, where the elements can be placed in a one-to-one correspondence with the natural numbers themselves. Uncountable infinity, on the other hand, refers to sets like the real numbers, where there are more elements than can be counted, even with an infinite sequence. Infinite sequences are arrangements of elements that continue forever. Mathematically, we often treat infinite sequences using limits, which allow us to study their behavior as they approach infinity. In infinite sets, paradoxes arise when we try to apply operations or assumptions that make sense for finite sets, but fail for infinite ones. For example, Hilbert's Hotel, a famous paradox, illustrates the counterintuitive properties of infinity. In Hilbert's Hotel, there are infinitely many rooms, all occupied. Yet the hotel can still accommodate new guests by moving existing guests around. This highlights the strange nature of infinity. Operations that seem impossible for finite systems are possible in the realm of infinite sets. Zeno's paradox takes a similar approach by considering the infinite nature of reality and how it might cause contradictions. According to the paradox, trying to apply the principles of finite logic to infinite sets leads to logical contradictions. As we explore infinite systems in more detail, we encounter contradictions in the relationship between sets, sequences, and real-world systems. Zeno's dichotomy paradox revolves around an infinite series of tasks that must be completed in a finite amount of time. If you are walking toward a door, you first cover half the distance, then half of the remaining distance, then half of the remaining distance, and so on. This creates an infinite sequence of steps that must be taken in order to reach the door. In mathematical terms, the distance you need to cover can be expressed as the sum of an infinite series. Total distance equals 1/2 plus 1/4 plus 1/8 plus 1/16 plus. The series is geometric in nature, where each successive term is half the value of the previous one. The sum of this infinite series can be calculated using the formula for the sum of a geometric series. S equals A/1.r, where A is the first term in the series, R is the common ratio. In this case, R equals 1/2. Substituting the values, we get S equals 1/2/1, meaning the total distance to the door is finite. Meaning the total distance to the door is finite, even though there are infinitely many steps to take. The paradox arises because, although we can mathematically add up the infinite series to get a finite result, Our intuitive understanding tells us that an infinite number of steps should prevent us from reaching the goal. The resolution to Zeno's paradox comes from the concept of limits in calculus. The idea is that even though there are an infinite number of steps to take, the total distance covered in those steps converges to a finite value. This is the essence of how we deal with infinite series in modern mathematics. The sum of an infinite series of diminishing values can still result in a finite number in terms of time. As you take each step, the amount of time you spend on each successive step becomes smaller and smaller. The total time taken to reach the destination is finite because the series of time intervals also converges to a finite value. In the real world, we experience motion as continuous rather than discrete. Even though we can conceptually divide motion into an infinite number of steps, the actual process of moving from one place to another involves smooth, continuous transitions. The dichotomy paradox reminds us that infinity is not a practical obstacle in motion, it's a mathematical abstraction. The paradox illustrates that while we can divide space and time into infinite parts, continuous motion allows us to reach the destination, even if the process involves an infinite sequence of steps. The dichotomy paradox has important implications in theoretical physics and engineering, especially in areas like quantum mechanics and signal processing. In these fields, systems are often modeled using infinite series or continuous processes. Understanding how infinite processes can result in finite outcomes is crucial for designing precise calculations in engineering and predicting physical behavior in quantum systems. The paradox also has profound philosophical implications for how we understand the nature of time, change, and motion. It raises the question, how can the infinite be contained within the finite? This paradox continues to inspire discussions about the nature of reality and how we conceptualize the passage of time and space. A Feynman sprinkler. Imagine a sprinkler system designed to shoot water outward in a neat circular spray. Now, what if we reverse it? Instead of water spraying outward, the sprinkler is sucking water inward, as though it's trying to draw the water back into itself. This should result in the sprinkler moving in the opposite direction, right? Well, according to Richard Feynman's paradox, the answer is not so simple. If you reverse the direction of the water flow in the sprinkler, you would intuitively expect the sprinkler to move backward, propelled by the force of the water being sucked in. But surprisingly, under ideal conditions, it doesn't move at all, or it might even move in the opposite direction. The Feynman sprinkler paradox challenges our understanding of fluid dynamics and the conservation of momentum. Why doesn't the reversed sprinkler behave as we expect, moving backward as the water is drawn in? Let's dive into the Feynman sprinkler paradox, where the relationship between water flow, motion, and momentum defies our expectations. The Feynman sprinkler paradox is named after Richard Feynman, the renowned physicist, who introduced this thought experiment while discussing the principles of fluid dynamics and momentum. Feynman, known for his quantum electrodynamics work and engaging teaching style, often posed intriguing problems to illustrate key concepts in physics. The paradox involves a seemingly simple device, the sprinkler, and explores how the flow of fluids can lead to counterintuitive results. The paradox emerged from Feynman's work on hydrodynamics and his ability to apply conservation laws to everyday objects. The thought experiment is simple, yet puzzling. Imagine a typical sprinkler system that ejects water outward. Now reverse the system such that water is being sucked in instead of sprayed out. Intuitively, one would expect the sprinkler to move backward as the water is drawn inward due to the reactionary force, similar to how a rocket works. However, Feynman pointed out that under idealized conditions involving perfect symmetry and ideal fluid flow, the sprinkler does not behave as expected. This paradox draws attention to the subtle effects of fluid behavior, including momentum transfer, the effects of vortex formation, and how real-world deviations from ideal conditions complicate the situation. It challenges both classical fluid dynamics and our intuitive understanding of how forces act on objects, making it a fascinating topic for further study in physics and engineering. The Feynman sprinkler paradox challenges our understanding of fluid dynamics by exploring how water flow can create seemingly counterintuitive motion. At first glance, it appears that a reversed sprinkler, one that sucks water in, should move backward as the water is drawn into it. However, Feynman's paradox reveals that under idealized conditions, this behavior does not occur in the expected way. Let's break down the paradox, the forces involved, and how we can resolve it, using principles of fluid mechanics and momentum conservation. 1. the setup of the Feynman sprinkler paradox. The Feynman sprinkler paradox begins with a typical sprinkler system, which is designed to spray water outward in a radial direction. The system typically operates by forcing water through small nozzles, causing the water to exit at high velocity, creating a spray pattern. In the paradox, we reverse this situation. Instead of the sprinkler spraying water outward, we imagine that the water is being sucked inward into the nozzles of the sprinkler. According to the conservation of momentum, as water is drawn into the sprinkler itself should move in the opposite direction, much like how a rocket moves when fuel is expelled backward. This idea is based on the third law of motion, which states that for every action there is an equal and opposite reaction. The suction of water should cause the sprinkler to move backward, just as a rocket is propelled in the opposite direction when it expels exhaust gases. The initial expectation is that if the system is perfectly symmetrical and the flow is idealized, the sprinkler will move backward, proportional to the rate of water intake. However, as Feynman pointed out, the sprinkler does not exhibit this behavior. In fact, it behaves quite differently under ideal conditions, leading to the paradox. A. Conservation of momentum in fluids. The conservation of momentum is a key principle in understanding why the Feynman sprinkler paradox leads to unexpected results. In the case of a rocket, fuel is expelled backward and the rocket is pushed forward as a result. This is an example of momentum transfer. The momentum of the expelled fuel is transferred to the rocket, propelling it forward. In the case of the reversed sprinkler, however, the situation is more complicated. The suction of water is not as simple as expelling gas or liquid from a rocket. The water entering the nozzle will be accelerated by the pressure difference. But the way in which momentum is transferred through the water is influenced by several factors, including the geometry of the sprinkler and the nature of the flow. B. The role of vortices and symmetry. In the case of the reversed sprinkler, a vortex forms in the water as it is drawn inward. The vortex is a rotating flow pattern that arises when fluid moves in a circular path around an axis. This vortex redistributes the momentum in the system in a way that is different from the expected reactionary force. The ideal symmetry of the sprinkler system, where water flows inward uniformly through each nozzle, might not be perfectly achieved, which means the forces that should create a backward motion are not evenly distributed. The vortex effect causes the momentum to be distributed differently than anticipated, leading to the paradoxical situation where the sprinkler does not move backward as expected. Instead, the forces from the inward water flow tend to cancel each other out, or result in no net force acting on the sprinkler. 2. The behavior of fluids in idealized and realistic conditions. A. Ideal fluid flow versus real fluid flow. The paradox assumes idealized conditions, meaning we treat the fluid as inviscid, without viscosity, and assume perfect symmetry in the water flow. Under these ideal conditions, the forces acting on the sprinkler cancel each other out, leading to no net motion. This is because the water entering the nozzle at a specific rate does not impart a directional force that can be transferred to the sprinkler's body in the way we might intuitively expect. However, in real-world conditions, factors like viscosity, turbulence, and imperfections in the system, such as uneven nozzle shapes or water resistance, would contribute to a slightly different behavior. Real fluid dynamics involve non-ideal interactions, which would create some backward motion, but likely not in the dramatic way expected from the idealized system. B. Vortex breakdown and the effect of nozzle shape. In a real sprinkler system, the shape of the nozzles, the flow rate, and the surface texture of the sprinkler can all contribute to non-ideal fluid dynamics, vortex breakdown, where the rotating flow of fluid collapses or changes in intensity can affect the flow entering the nozzle, creating turbulence that may cause some degree of motion or resistance. The actual backward motion of the sprinkler might be a result of these small imperfections in the system, rather than the expected reactionary force from the suction itself. In contrast, the idealized system in the Feynman paradox assumes that such complexities are ignored, which results in the counterintuitive conclusion that the sprinkler does not move at all under perfect conditions. 3. Understanding the paradox, the real reason behind the lack of motion. A. Ideal fluid assumptions and momentum redistribution. The paradox arises from the assumption that in an ideal fluid there is no friction or resistance. This allows for perfect symmetry in the flow. However, in reality, the behavior of fluids is affected by viscosity, boundary layers, and turbulent flow, which redistribute momentum in a way that leads to small motions or discrepancies. In the case of the reverse sprinkler, the momentum from the inward flow of water is not transferred to the sprinkler body in the same way it would be for a rocket. The vortex motion created by the suction leads to a redistribution of forces that causes the sprinkler to behave differently than expected. Instead of propelling backward, the system stabilizes due to the perfect symmetry and the way momentum is shared among the different parts of the flow. B. Theoretical resolution, using fluid mechanics. The key to resolving the paradox lies in the fact that ideal fluid dynamics in an enclosed system like the reversed sprinkler does not produce a net reaction force. The symmetrical flow of water entering the nozzles does not result in the uneven pressure gradients that would propel the sprinkler backward. The perfect symmetry cancels out any potential backward motion, leading to no observable movement under ideal conditions. In real-world conditions, however, imperfections in the system would likely result in small movements due to fluid viscosity and the inherent asymmetry in the system. These factors would contribute to a small backward motion, but it would still be far less than what we might intuitively expect. 4. Real-world applications and implications of the Feynman sprinkler paradox. A. Engineering and fluid systems. The Feynman sprinkler paradox highlights the complexities of fluid systems and the limitations of idealized models. In engineering, systems involving fluids, such as pumps, turbines, and sprinklers, are designed using models that assume inviscid or ideal flow. However, real-world systems often deviate from these models due to factors like turbulence and viscosity, making the Feynman sprinkler a reminder of how real-world imperfections affect our understanding of fluid behavior. B. Fluid mechanics in microgravity and space systems. The paradox also has implications for fluid systems in microgravity environments, such as on the International Space Station, ISS. In the absence of gravity, fluids behave very differently, and understanding how water moves in a system where suction is involved becomes crucial. The principles demonstrated by the Feynman sprinkler can aid engineers and scientists in designing fluid-based systems for space missions, where precise control of liquid flow is essential for life support systems, fuel systems, and cooling systems. Hydrostatic paradox. Imagine you have two containers filled with water, both with the same depth of liquid. In one container, the water is stacked vertically in a single column, while in the other, the water is spread out horizontally across a large surface. Now, imagine placing a pressure gauge at the bottom of both containers. Intuitively, you might think that the pressure at the bottom would be greater in the container with the taller column of water, but according to the hydrostatic paradox, this is not always the case. In fact, the paradox suggests that the pressure at the bottom of each container is the same, regardless of the shape or arrangement of the water, as long as the depth is the same. The hydrostatic paradox challenges our intuition about fluid pressure and reveals the surprising fact that pressure is determined only by the depth of the fluid, not its volume or shape. How can the pressure at the bottom of two seemingly different containers be the same? Let's explore the hydrostatic paradox, where fluid pressure and depth behave in ways that defy our expectations of volume and shape. The hydrostatic paradox is a concept rooted in the study of fluid mechanics and the behavior of fluids under pressure. It is often attributed to Blaise Pascal, the famous French mathematician and physicist, who developed the foundational principles of hydrostatics. Pascal's work on the relationship between pressure and depth in fluid laid the groundwork for understanding how fluids behave in various environments. The paradox arises from the principle of hydrostatic pressure, which states that the pressure at a given depth in a fluid depends only on the density of the fluid and the depth of the fluid column above that point. This is described by the equation P equals GH, P equals RGH, where P is the pressure at depth HH, R is the density of the fluid, GG is the acceleration due to gravity, and HH is the depth of the fluid. Despite this simple relationship, the hydrostatic paradox challenges the intuition of how we perceive pressure in different fluid systems. It suggests that regardless of the shape or configuration of the fluid, as long as the depth remains constant, the pressure at the bottom will remain the same. This paradox has been discussed in the context of Pascal's law, which describes how pressure is transmitted uniformly in a fluid at rest. The hydrostatic paradox serves as a reminder that pressure is a function of depth, not the volume or shape of the container. challenging common assumptions about how fluids behave in different geometries. The hydrostatic paradox is a fascinating concept that arises from the fundamental principles of fluid statics, particularly the relationship between pressure and depth in a fluid at rest. The paradox appears counterintuitive at first because we often associate pressure with volume or shape, yet pressure in a fluid at rest depends solely on the depth of the fluid column, not its shape, surface area or volume. To understand the paradox, we need to explore the principles of hydrostatic pressure, the factors that determine fluid pressure, and the surprising implications of this principle for different fluid systems. 1. Understanding hydrostatic pressure. The definition of hydrostatic pressure. Hydrostatic pressure is the pressure exerted by a fluid at rest. It increases with depth because of the weight of the fluid above. The basic formula for hydrostatic pressure is given by P equals Geach P equals R Geach, where PP is the pressure at a given depth, R is the density of the fluid, GG is the acceleration due to gravity, and HH is the depth of the fluid at the point where the pressure is being measured. This equation tells us that the pressure at a depth in a fluid depends directly on the depth, HH, and the density of the fluid, R, but not on the volume or shape of the container. This is the fundamental idea behind Pascal's law, which asserts that pressure is transmitted uniformly in all directions through an incompressible fluid. The paradox arises when we think about different shapes and configurations of fluid containers. Common sense might suggest that taller columns of fluid would create greater pressure at the bottom, while more spread out fluids would exert less pressure. However, according to hydrostatic principles, depth alone determines pressure. B. The role of depth in pressure. The depth of the fluid is the primary determinant of the pressure experienced at the bottom of the container. Regardless of whether the fluid is in a tall, narrow column or a wide, shallow pool, the pressure at the same depth is the same. This is because, in both cases, the fluid at that depth has the same column height above it, exerting the same weight on the fluid below. This principle holds true for any shape of container, as long as the depth at a given point remains unchanged. The volume, or horizontal spread of the fluid, does not affect the pressure at a particular depth, because the weight of the fluid above that point is what determines the pressure. 2. The paradox. Comparing containers of different shapes. A. The tall, narrow column versus the wide, shallow container. To understand the hydrostatic paradox, let's consider two containers filled with water. Both containers have the same depth of water, but their shapes are different. Tall, narrow column. One container is shaped like a tall, narrow column, with the water reaching a certain depth, say 1 meter. Wide, shallow container. The other container is shaped like a wide, shallow pool, with the same water depth of 1 meter, but the water is spread across a much larger surface area. In the first container, the water is confined to a small space, while in the second container, the water is spread out over a wide surface area. Intuitively, you might think that the taller column of water exerts more pressure at the bottom, because it contains more water and has a greater volume of fluid above. However, according to the hydrostatic paradox, the pressure at the bottom of both containers is the same, because the depth of water is the same in both cases. In the narrow column, the pressure is determined by the height of the water column, 1 meter, and in the wide pool, the pressure at the bottom is still determined by the same depth of water. The shape or volume of the container does not affect the pressure at the bottom. The only thing that matters is the depth of the fluid. This is the key insight behind the hydrostatic paradox. B. Implications for different fluid systems. This paradox has important implications for understanding fluid systems in real-world applications. For instance, in hydraulic systems, pressure is crucial in determining how fluid will behave within the system. Engineers often rely on the principle that pressure is determined by depth, not by the size or shape of the container, when designing systems for water transport, pumps and pressurized vessels. It also highlights the importance of hydrostatic pressure in systems like dams and barriers, where the pressure exerted by a fluid is related only to the depth of the fluid, not its volume or surface area. 3. Mathematical and physical insights into the paradox. A. The steady-state fluid flow, the hydrostatic paradox, can be further understood by recognizing that in a steady-state fluid, a fluid that is not moving, the pressure is constant at a given depth, and the fluid's momentum does not come into play. The water molecules exert pressure in all directions, but the horizontal distribution of the fluid does not affect the vertical pressure at a given depth. This steady-state behavior is key to resolving the paradox. Since the pressure depends only on the depth of the fluid and not on its shape or volume, the horizontal extent or volume of the container does not influence the pressure exerted at the bottom. The fluid is in equilibrium, with no movement that would create additional forces or gradients in pressure. B. The pressure distribution in both containers. The pressure is distributed evenly across the bottom, and the fluid behaves in the same way regardless of the container's size or shape. As the depth increases, the pressure increases proportionally, but the horizontal spread of the fluid does not change this relationship. This principle also applies in more complex systems where fluids are interacting with solid surfaces, such as liquids in tanks or fluids within porous materials. The depth-based pressure remains constant as long as the fluid is in hydrostatic equilibrium. 4. Real-world applications of the hydrostatic paradox. A. Fluid statics in engineering and design. The hydrostatic paradox has real-world applications in engineering, particularly in fluid statics and hydraulic engineering. For example, the design of pressure vessels, dam walls, and water storage systems relies on the understanding that the pressure at depth is independent of the shape or volume of the container. In these systems, engineers use the principle of hydrostatic pressure to calculate the forces exerted on the structure and ensure its stability. B. Atmospheric pressure and the shape of the Earth. Another application of the hydrostatic paradox can be found in understanding atmospheric pressure. The Earth's atmosphere is a vast fluid system, and the pressure at any point on the surface of the Earth depends only on the height of the air column above it, not on its horizontal spread. This is why the atmospheric pressure at sea level is similar across vast distances, even though the landscape and air volume vary widely. 5. Philosophical implications of the paradox. The hydrostatic paradox challenges our intuition about how pressure works in fluids. It forces us to reconsider the relationship between shape, volume, and pressure. It suggests that our everyday understanding of fluids, where we often expect more fluid to lead to more pressure, is not entirely accurate when it comes to hydrostatics. This paradox also ties into philosophical discussions about how we perceive and model the physical world. It highlights the importance of idealized models in understanding complex systems, and how our perceptions of reality are often shaped by abstract mathematical principles. Norton's dome paradox. Imagine a small ball resting at the peak of a dome-shaped surface. Now, what happens if you nudge the ball ever so slightly? In classical mechanics, we would expect the ball to roll down the dome, propelled by gravity, toward the lowest point. But here's the twist. Norton's dome paradox suggests that, under certain conditions, the ball might remain perfectly still at the top of the dome, never moving, despite being in a position where, in most scenarios, motion is inevitable. The paradox arises when we consider a system where determinism, the idea that future events are fully determined by past states, and free will, the ability to choose or change the course of events, seem to conflict. The ball's motion, or lack thereof, is determined by the initial conditions, yet the laws of physics appear to give rise to a situation where no motion occurs. Norton's dome paradox forces us to reconsider the concepts of determinism and predictability in classical mechanics, raising critical questions about the nature of physical laws and the role of free will in a seemingly deterministic world. Let's explore this counterintuitive paradox, where physics seems to break down in an unexpected way. Norton's dome paradox was proposed by John D. Norton, a philosopher and physicist, to illustrate a fascinating problem in the realm of determinism and free will within classical mechanics. Norton's paradox is specifically designed to challenge our understanding of determinism, a concept in which the state of the world at any given time determines everything that will happen in the future, leaving no room for randomness or unpredictability. The paradox uses a theoretical dome-shaped surface, a smooth, frictionless surface on which a ball is placed at the top. The idea is that, based on Newtonian mechanics, the ball should begin to roll down the dome due to gravity. It highlights a situation in which the evolution of a system seems to contradict our understanding of Newtonian physics, leading to a paradoxical situation where, despite being in a state that should naturally evolve, no motion occurs. 1. The setup of Norton's dome paradox. Norton's dome paradox begins with a simple physical system, a ball placed at the top of a dome-shaped surface. The surface of the dome is smooth and frictionless, meaning that there is no resistance to the ball's motion, and the ball is only affected by the force of gravity. In most cases, we would expect the ball to roll down the dome due to gravitational attraction, with its motion governed by Newton's laws of motion. However, in Norton's dome, the shape of the dome is carefully chosen to create a system that defies expectation. The key feature of this dome is that the ball's position at the top of the dome is unstable in a particular way, leading to a peculiar result. When the ball is placed at the top of the dome and given a very small nudge, it does not start moving. In a more detailed setup, the dome is perfectly symmetrical at the top, and the ball has no initial velocity. According to classical mechanics, when the ball is nudged, we expect it to roll down the dome, as gravity should cause the ball to accelerate in the direction of the steepest slope. But the paradox arises because the ball does not move under these conditions, even though the system is fully deterministic. The shape of the dome. To fully understand the paradox, it is essential to examine the shape of the dome. The dome is specifically designed so that it is locally flat at the top, with the ball sitting perfectly still. The geometry of the dome is such that, at the very top, the potential energy of the ball is minimal, and the system is in equilibrium. However, the paradox is that even though this is an equilibrium point, it is unstable. A small nudge could push the ball into motion. In standard physical systems, this type of instability leads to the object moving, but in this case, the perfect symmetry of the setup results in the ball staying still. 2. The paradox. Motion or lack thereof. The core of Norton's dome paradox is that, in a perfectly deterministic system, the ball should either remain stationary or start rolling down the dome once nudged. But here, the ball remains stationary, despite no forces acting in such a way that would lead to its motion. We might intuitively expect that the force of gravity would cause the ball to begin rolling, but due to the symmetry and the specific configuration of the dome, the system does not evolve as we expect. This is a deterministic paradox. In a deterministic system, the future state of the system is completely determined by its initial conditions. The ball starts at a specific point, with no velocity, at the top of the dome. By classical mechanics, we would predict that the ball should begin rolling down the dome, due to the force of gravity, but instead, we find that the ball remains stationary. The role of determinism. Norton's dome challenges our understanding of determinism by suggesting that even in a system where the future state is theoretically predictable from the initial conditions, there can be situations where the system does not evolve as expected. The paradox highlights a situation where no change occurs despite the deterministic nature of the system. The problem with predictability. The paradox raises a key question. If a system is deterministic, why doesn't it evolve predictably? The paradox suggests that, even though the system is theoretically deterministic, the specific initial conditions, such as the position of the ball at the top of the dome, might lead to a situation where the future state is indeterminate. The ball, at the top of the dome, is at a local minimum in potential energy. There is no initial force acting to displace the ball, yet the system is still deterministic in its overall nature. This creates a logical contradiction. Under classical physics, if an object is at rest and no external forces act on it, it should remain at rest. However, because of the shape of the dome, the system fails to evolve, and the paradox lies in this very contradiction. 3. Resolving the paradox. The role of symmetry and instability. Symmetry and the stability of the equilibrium. In classical mechanics, the stability of an equilibrium is determined by whether small perturbations, nudges, will lead to motion or will keep the system at rest. The equilibrium at the top of Norton's dome is unstable. Any small change in position will lead to a departure from equilibrium, resulting in motion. However, in the case of this particular dome, the symmetry of the system ensures that no motion occurs. This paradox is a logical consequence of the specific geometry of the dome and the way deterministic laws are applied. It shows that even in a system that seems to be governed by clear and predictable laws, small instabilities in the system can result in behavior that defies our expectation. Understanding the stability of systems, the Norton dome paradox, can be understood in terms of the behavior of unstable equilibria in physics. While in most systems, small changes in position lead to motion, In this case, the symmetry of the dome creates a unique situation where motion does not occur. The paradox reveals that our concept of determinism might be more complex than it seems, especially when instabilities in a system prevent predictable outcomes. 4. Philosophical implications of Norton's dome. A. Free will and determinism. One of the most intriguing aspects of Norton's dome paradox is its philosophical implications for free will and determinism. The paradox suggests that, even in a fully deterministic world, there may be situations where the future fails to unfold predictably due to the nature of the system's geometry. This raises important questions about the determinism of physical systems and the role of free will in a world governed by physical laws. Does the lack of motion in the dome suggest that free will plays a role in determining outcomes? Or does it reveal that even in a deterministic universe, future events can be unpredictable in certain situations? B. The limits of classical mechanics. Finally, the Norton dome paradox highlights the limits of classical mechanics in explaining all aspects of physical reality. While classical mechanics is often highly successful in describing many systems, the paradox suggests that there may be intrinsic uncertainties in the application of deterministic laws to certain situations, challenging the absoluteness of Newtonian determinism. However, in Norton's dome, the shape of the dome is chosen in such a way that, under certain initial conditions, the ball does not move at all. This creates a contradiction within the framework of deterministic physics, where we expect the system to evolve in a predictable way, yet the ball's motion seems to be indeterminate. Norton's dome paradox is often discussed in the context of philosophical discussions on free will and determinism, because it appears to show that, even in a perfectly deterministic system, there can be situations where no evolution occurs. The paradox highlights the tension between our intuitive understanding of the laws of motion and the more abstract conceptual frameworks that govern reality. It remains an important example of how classical mechanics might give rise to counterintuitive outcomes, providing insights into the philosophy of science and the nature of deterministic systems. Norton's dome paradox is a thought experiment that forces us to confront some deeply held assumptions about the nature of determinism and predictability in classical mechanics. Paine-Levy paradox. Imagine a small object moving through space, following a smooth and predictable path. Now, what if I told you that as the object moves, its path begins to bend and twist, creating singularities that defy normal physical laws? This is at the heart of the Paine-Levy paradox, a thought experiment that arises when we apply nonlinear dynamics to classical mechanics, particularly when considering systems that involve singularities, points where a function becomes undefined or exhibits infinite behavior. The paradox is named after the French mathematician Paul Paine-Levy, who studied differential equations and their behavior near singular points. Paine-Levy's paradox demonstrates that even within the well-established framework of Newtonian mechanics, seemingly smooth systems can give rise to unpredictable, chaotic behavior. The paradox raises the question: how can we reconcile the elegant equations of classical mechanics with the singularities and non-linearities that seem to disrupt them? Let's explore the Paine-Levy paradox, where smooth motion leads to singular chaos, challenging our understanding of determinism and predictability in classical physics. The Paine-Levy paradox is named after Paul Paine-Levy, a French mathematician and physicist who made significant contributions to the study of differential equations and their applications in physics. Paine-Levy was particularly interested in the behavior of non-linear dynamical systems, which often exhibit singularities, points where the system's behavior becomes undefined or explodes. Paine-Levy's work on these systems revealed that even in classical mechanics, where the equations of motion are well understood, there can exist solutions to these equations that are non-smooth and lead to singularities. These singularities are points where the differential equations governing the system break down, often leading to unpredictable or chaotic behavior. The Paine-Levy paradox is the idea that such singularities can arise in systems that, at first glance, appear to follow deterministic laws and exhibit smooth motion. Paine-Levy's study of nonlinear dynamics has become foundational in modern physics, particularly in fields like chaos theory and complex systems, where singularities play a critical role in understanding the evolution of systems over time. The paradox, however, serves as a reminder that deterministic laws in classical mechanics can lead to nonlinear behavior that challenges our expectations of predictability and smooth evolution. Painleave's work on the paradox laid the groundwork for further studies on how singularities and chaotic systems emerge, even in deterministic frameworks. The Painleave paradox exposes a surprising aspect of nonlinear dynamics within classical mechanics. At first glance, we expect physical systems governed by deterministic laws, such as the laws of motion or gravity, to follow smooth, predictable paths. However, the paradox reveals that even deterministic systems can give rise to singularities, points where the equations governing the system break down and lead to chaotic behavior. Let's break down the paradox, the key concepts of singularities and nonlinear dynamics, and how they arise in physical systems. 1. The setup of Painleave paradox. Nonlinear systems and singularity A. Classical mechanics and predictability. Classical mechanics is grounded in the deterministic equations of motion established by Newton. These equations describe how objects move through space based on forces applied to them. In this framework, the future state of a system is fully determined by its current state, and the equations of motion provide a smooth, continuous description of an object's trajectory. For most systems, we can predict an object's motion at any time in the future, given its initial position and velocity. However, certain nonlinear systems defy this predictability and give rise to singularities. A nonlinear system is one in which the relationship between variables is not directly proportional and can lead to complicated and unpredictable dynamics. These non-linearities can cause a system to exhibit behavior that seems irregular, chaotic, or even mathematically undefined at certain points. The Painleave paradox arises when systems governed by non-linear equations exhibit singularities, points at which the system's behavior becomes undefined. In classical mechanics, this can occur in perfectly deterministic systems, which should, theoretically, evolve smoothly according to the laws of physics. When singularities appear, they disrupt the expected smooth motion, challenging our understanding of predictability and determinism in these systems. B. The idea of singularities in mathematics. A singularity in mathematics refers to a point where a function or equation becomes undefined or exhibits infinite behavior. For example, a function may have a vertical asymptote, where it increases without bound as it approaches a particular point. In the context of physical systems, a singularity might correspond to a situation where a variable, such as velocity or force, grows infinitely large or becomes undefined. In differential equations, which describe the motion of physical systems, singularities often occur when the solutions to these equations become non-physical or inconsistent. This can happen in non-linear systems, where small changes in initial conditions can lead to disproportionate effects, resulting in a blow-up of the solution, where the variables involved take on infinite values. The Painleave paradox demonstrates that singularities can arise in systems that are otherwise deterministic and smooth in nature, leading to chaotic behavior that seems to defy physical laws. 2. The nature of nonlinear dynamics and singularities in physical systems. A. Nonlinear systems and chaos. In nonlinear dynamics, the behavior of a system is governed by equations that involve nonlinear terms, meaning the relationship between variables is not proportional or linear. These systems can be highly sensitive to initial conditions, meaning that even small changes in the starting state can lead to vastly different outcomes. This sensitive dependence on initial conditions is a hallmark of chaos theory, which explores how deterministic systems can evolve into chaotic behaviors that are difficult to predict. While many nonlinear systems exhibit chaotic motion, singularities present an even more dramatic breakdown of predictability. Singularities in a system can cause variables like velocity or acceleration to become infinite, leading to undefined behavior that seems inconsistent with the laws of physics. For example, in a nonlinear pendulum, the motion of the pendulum is influenced by gravitational forces and angular displacement. In most cases, the motion can be described by smooth, predictable equations. However, if the system is disturbed in certain ways, it may reach a singularity, where the angular velocity or force becomes infinite. This results in a paradox where, even though the system follows deterministic laws, its behavior becomes mathematically undefined at a particular point. B. Painleaf's study of singularities. Paul Painleaf studied the behavior of nonlinear differential equations, particularly those that arise in the context of mechanical systems. He developed a series of equations to describe systems in which singularities appear, particularly focusing on second-order differential equations that describe the motion of objects. Painleaf was interested in understanding how singularities arise in systems that should otherwise behave smoothly and predictably. The Painleaf paradox specifically refers to the apparent contradictions that arise when a deterministic system, governed by Newton's laws, experiences a singularity. These paradoxical situations challenge the idea that deterministic systems should always lead to smooth, predictable behavior, and raise important questions about the limits of predictability in nonlinear systems. 3. A thought experiment. The ball and the dome. One way to visualize Painleaf's paradox is through a thought experiment involving a ball placed at the top of a dome. In this experiment, we imagine a smooth, frictionless dome where the ball, initially at rest, is free to roll down the surface due to gravity. In a normal system, the ball would roll down the dome and follow a predictable path determined by classical mechanics. However, in this scenario, we introduce a non-linear interaction at the top of the dome. This causes the ball's motion to become unstable, and instead of following the expected path, the ball exhibits singular behavior. For example, the ball might remain stationary at the top, or its motion might become chaotic and unpredictable. The paradox emerges because, despite the deterministic nature of the system, the ball's behavior is no longer predictable, and it may violate the standard laws of motion. This thought experiment shows that even in deterministic systems, singularities can emerge, leading to behavior that seems at odds with our expectations of smooth motion. The Painleaf paradox suggests that in certain non-linear systems, the laws of physics do not always produce predictable, smooth results, and chaotic behavior or singularities can arise unexpectedly. 4. Resolving the paradox. The role of regularization and mathematical solutions. A. The regularization of singularities. One way to resolve the Painleaf paradox is through the technique of regularization, which involves finding ways to redefine or modify the equations governing a system to remove or smooth out the singularities. This approach is common in theoretical physics, where singularities are often seen as mathematical artifacts that can be handled by reinterpreting the system. In the case of n-body problems or gravitational systems, physicists use regularization techniques to remove the infinite forces or velocities that arise when objects get too close to each other. Similarly, in nonlinear systems, mathematicians can find solutions to the differential equations that avoid the explosive behavior at the singularity, allowing the system to continue evolving predictably. B. Understanding the limits of determinism. While deterministic systems are often thought to be fully predictable, the Painleaf paradox forces us to reconsider this assumption. The paradox suggests that in some cases the behavior of a system might be indeterminate or chaotic, even though it is governed by deterministic laws. This points to the limits of classical determinism and the importance of understanding the complexities of nonlinear dynamics. 5. Real-world applications and implications. A. Chaos theory and nonlinear systems. Many physical systems, from weather patterns to fluid dynamics, exhibit chaotic behavior that is sensitive to initial conditions. The paradox reminds us that even in deterministic systems, nonlinear interactions can lead to unpredictable behavior. B. Philosophical implications of free will and determinism. The paradox also raises questions about the nature of determinism and free will. If a system governed by deterministic laws can lead to singularities or chaotic behavior, it challenges our expectations of predictability and raises important philosophical questions about the limits of determinism and the role of free will in a deterministic universe. Stokes' paradox. Imagine you have a small ball moving through a thick fluid, like honey or oil. Intuitively, you might think that the ball's movement will be slowed down by the resistance of the fluid. Now, imagine that you're looking at this situation in a two-dimensional world, where the fluid only flows in 2 dimensions, like a flat sheet. The result, Stokes' paradox suggests that, in such a two-dimensional flow, the ball's motion is undisturbed by the fluid's viscosity, and the resistance you might expect simply doesn't arise. The paradox was first proposed by the renowned physicist George Stokes, and it highlights a seemingly counterintuitive result in fluid dynamics. In a two-dimensional flow, viscous forces behave differently than in three dimensions, leading to an outcome where theoretically, a small object in a viscous fluid would experience no drag at all. The paradox raises important questions about the nature of viscosity, drag, and the geometry of fluid systems. How can a system that we expect to experience resistance instead behave in a way that defies common sense? Let's dive into Stokes' paradox, where fluid viscosity and two-dimensional flow challenge our understanding of drag and resistance. Stokes' paradox was formulated by the Irish physicist George Stokes in the mid-19th century, and it revolves around the behavior of viscous flow in two-dimensional fluid systems. Stokes was investigating how fluids behave when they flow past an object, like a small sphere, under the influence of viscosity. In a typical three-dimensional fluid, the interaction between the fluid and the object creates drag and resistance, which slow the object's motion. Stokes was well known for his work in fluid dynamics, and he made significant contributions to the understanding of viscous flows and Stokes flow, especially for low Reynolds number flows, where fluid inertia is negligible compared to viscous forces. However, when he applied his knowledge to a two-dimensional flow, he encountered a surprising result. In two-dimensional space, viscous drag on a small object, like a sphere, is zero. This is in contrast to the intuitive expectation that the viscosity of the fluid should exert resistance, slowing down the object. The paradoxical result was that, in two dimensions, there's no resistance for the object as it moves through the fluid. Stokes' paradox thus reveals the strange behavior of viscous flow in low-dimensional systems, and was an early exploration into the complexities of fluid dynamics. While the paradox holds for idealized two-dimensional models, it serves to deepen our understanding of drag forces and the nature of viscous fluids. The paradox has since influenced many later developments in fluid mechanics, including work on boundary layers and turbulence. Stokes' paradox explores the behavior of fluids under the influence of viscosity, especially in the context of two-dimensional flows. While we intuitively associate viscous drag with the movement of objects through fluids in three-dimensional space, the paradox reveals that, in a two-dimensional fluid, a small object experiences no resistance at all, an outcome that seems counterintuitive. To understand the paradox, we need to break down the core concepts of fluid viscosity, Reynolds number, and two-dimensional dynamics. 1. The concept of viscous flow in three dimensions, viscosity and drag in fluids. In typical fluid dynamics, when an object moves through a viscous fluid, it experiences resistance due to the internal friction of the fluid. This resistance is commonly referred to as drag and is primarily caused by viscous forces acting between the layers of the fluid. Viscosity is a property of a fluid that quantifies its resistance to flow. In essence, how thick or sticky the fluid is. For example, water has a relatively low viscosity compared to honey, which is much thicker. When an object, such as a sphere, moves through a viscous fluid, the fluid layers near the surface of the object move slower due to friction, creating a velocity gradient between the object and the surrounding fluid. This gradient creates shear forces that act to slow down the object, and the object's motion is impeded by these viscous forces. The magnitude of the drag force on the object depends on several factors, including the speed of the object, the fluid's viscosity, and the size of the object. The classic expression for the drag force on a sphere moving through a fluid in three-dimensional space is given by the Stokes drag equation. Fd equals 6rv, where Fd is the drag force, is the viscosity of the fluid, r is the radius of the sphere, v is the velocity of the object. This equation tells us that as the object moves through the fluid, the drag force is proportional to the velocity of the object, the fluid's viscosity, and the object's size. This relationship holds for low Reynolds numbers, where viscous forces dominate over inertial forces. B. Reynolds number and flow regimes. The Reynolds number is a dimensionless quantity used to predict the flow regime in fluid dynamics. It is given by Re equals VL slash, where is the density of the fluid, V is the velocity of the object, L is the characteristic length, typically the radius of the object, is the viscosity of the fluid. For low Reynolds numbers, Re Ln1, the fluid is dominated by viscous forces, and the flow is laminar and smooth. In this regime, the drag force on an object can be described by Stokes' law. For high Reynolds numbers, pKcn 1000, inertial forces dominate, and the flow becomes turbulent, leading to different behavior and larger drag forces. In the case of the Feynman sprinkler paradox discussed earlier, we saw the effects of fluid flow in a system with low Reynolds numbers. Similarly, Stokes' paradox is based on the low Reynolds number assumption, where the fluid's viscosity dominates the flow, but with an important distinction. The flow is considered in 2 dimensions, not 3. 2. The two-dimensional flow setup A. The geometry of two-dimensional flow. In the context of Stokes' paradox, we consider a two-dimensional fluid, a fluid that flows in only 2 dimensions, like a flat plane. The geometry of this system is fundamentally different from the 3-dimensional case, where fluid can move in all directions. In a 2-dimensional flow, the fluid exists in a plane, and the object is moving through a fluid sheet rather than a full volume. This 2-dimensional flow is often modeled by idealized systems such as infinite planes or 2-dimensional containers. The key difference from 3-dimensional flow is that in 2 dimensions there is no third axis for the fluid to flow into or around. Therefore, the behavior of the fluid is restricted to a single plane, and the velocity profile is entirely different. In a 2-dimensional world, we would expect that the fluid would behave more like a thin sheet, and the resistance to the object's motion should behave differently. For example, in 3-dimensional flow, the drag on the object results from the viscosity of the fluid, where layers of fluid interact with each other. In 2 dimensions, however, the fluid flow is constrained in such a way that the velocity gradient around the object behaves differently. B. The impact of 2-dimensional flow on drag. The most surprising result from Stokes' paradox is that, in 2-dimensional flow, the drag force on a small object, such as a ball, vanishes. Unlike in 3 dimensions, where the viscous forces create resistance and slow down the object, in 2-dimensional flow, the fluid layers near the surface of the object do not exert the same type of drag force. This is because, in 2 dimensions, the flow behaves in a fundamentally different way. The object is moving through a sheet of fluid, and the frictional forces that normally slow the object down are no longer present in the same form. 3. The paradox. Why does drag vanish in 2 dimensions? A. Lack of frictional forces in 2 dimensions. In a typical 3-dimensional flow, as an object moves through the fluid's layers interact and create frictional forces that resist the object's motion. In 2 dimensions, however, these interactions are limited to the plane of the fluid, and the frictional forces are not as significant. As a result, the object experiences no drag in the same way it would in a 3-dimensional system. In the absence of a 3rd dimension, there are fewer ways for the fluid to transfer momentum from the object to itself. The fluid layers slide past each other with much less interaction, leading to the absence of the drag forces that are usually responsible for slowing down the object. B. Theoretical implications. The fact that no drag occurs in 2-dimensional flow has significant implications for how we understand viscous systems in general. Stokes' paradox suggests that, even in an idealized fluid system where viscosity is a key player, the geometry and dimensions of the system can drastically affect the way viscosity influences motion. In 3-dimensional systems, drag and resistance are inherently tied to the fluid's viscosity, but in 2-dimensional systems, the nature of fluid flow is so constrained that traditional notions of drag break down. This result is not just an academic curiosity. It reveals the limits of classical fluid dynamics in describing systems with reduced dimensions and provides insights into how fluid flow behaves in low-dimensional systems. 4. Resolving the paradox, the role of dimensions in fluid systems. A. Higher dimensional fluids and real-world applications. The Stokes paradox has practical implications for how we model fluid flow in lower dimensional systems, such as microfluidics, where fluids are often confined to very thin layers or narrow channels. Understanding how fluids behave in 2 dimensions can inform the design of nanodevices, where the effects of viscosity and drag are vastly different from those experienced in bulk flow systems. The paradox also highlights the need for more generalized models of fluid behavior that account for both dimensional constraints and the viscosity of fluids. In real-world systems, most fluids exist in 3 dimensions, and drag forces are important. However, when fluids are constrained to thin layers or 2-dimensional environments, the traditional principles of viscous drag may not apply, necessitating the development of more sophisticated models to describe these systems. Tea leaf paradox. Imagine a river flowing downstream, and at some point a contamination source is introduced into the water. Typically, we would expect the contamination to spread downstream with the flow of the water traveling in the same direction. But here's the twist. In the upstream contamination paradox, this intuition is challenged. What if contamination could travel upstream, against the current, seemingly defying the natural flow of water? How can a contaminant travel against the very forces that are pushing everything downstream? This paradox arises from the complex dynamics of fluid systems, where the introduction of a contaminant in a flowing stream or river can lead to counterintuitive effects, particularly in systems with non-linear flows, eddy currents, or turbulent mixing. The paradox reveals how fluid dynamics, particularly in open channels like rivers or oceans, can lead to contamination behaving in ways that defy common assumptions about directionality and flow. Let's explore the upstream contamination paradox, where non-linear fluid dynamics and contaminant transport combine to create unexpected results in the movement of pollutants in natural systems. The upstream contamination paradox is not a specific thought experiment or principle directly named in the works of a prominent scientist, but rather a complex, counterintuitive phenomenon in fluid dynamics and environmental science. The paradox arises in the context of contaminant transport in natural water systems, such as rivers, lakes, and oceans, where fluid flow and the spread of pollutants are studied. The paradox is rooted in the principles of fluid mechanics, advection, diffusion, and non-linear dynamics, which describe how substances, including contaminants, are carried by the movement of fluid. In many classical fluid systems, we intuitively expect contaminants to follow the direction of flow, typically downstream or in the direction of the current. However, in natural systems, the turbulence and eddy currents present in rivers or oceans can create situations where contaminants move upstream or against the main direction of flow. This phenomenon is influenced by factors such as local mixing, fluid turbulence, and the boundary conditions of the riverbed or shoreline, which can create non-linear effects that reverse or complicate the expected flow. While the paradox has been studied in the context of pollution control and environmental science, it's also relevant in fields like hydrodynamics, meteorology, and engineering, where the behavior of fluid transported substances needs to be understood. The upstream contamination paradox underscores the complexities of real-world fluid systems and serves as a reminder of how seemingly predictable systems can lead to unexpected outcomes. The upstream contamination paradox explores a scenario in which the behavior of contaminants in a flowing river or water system defies intuitive expectations. Normally, we assume that contaminants, when released into a fluid system, will be carried downstream with the flow. However, this paradox arises when contaminants seem to defy the direction of flow, traveling upstream or in the opposite direction of the flow. This paradox draws attention to the complexity of fluid dynamics, especially in systems with turbulence, eddies, and non-linear behavior. Let's break down the paradox, the mechanisms that lead to this counterintuitive behavior, and the mathematical framework that describes the transport of contaminants in fluid systems. 1. The basic concept of fluid flow and contaminant transport. A. Classical fluid flow, advection and diffusion. In classical fluid dynamics, the transport of substances within a fluid is often described by the advection-diffusion equation, which combines two primary mechanisms. Advection, the movement of particles or contaminants with the fluid flow. In this case, the contaminant moves downstream with the flow of the river or water system. Diffusion, the spread of particles due to random motion, causing the contaminant to spread in all directions, even opposite to the direction of flow. The standard advection-diffusion equation in its simplest form is Ct plus uxx equals d2 cx2 tc plus uxx 2c, where cxx2x is the concentration of the contaminant at position xx and time tt. Uu is the velocity of the flow, dd is the diffusion coefficient, cxxc represents the spatial gradient of the contaminant concentration, and 2cx2x22c represents the diffusion term. In a simple scenario, advection would transport the contaminant downstream, while diffusion would cause the contaminant to spread, including in the upstream direction. However, diffusion alone is not typically enough to carry the contaminant upstream, unless specific conditions are met. B. Non-linear behavior in fluid systems. In real-world fluid systems like rivers or oceans, the flow is rarely smooth and linear. Instead, turbulence and eddies, vortices of fluid that rotate and move in circles, create non-linear dynamics in the fluid flow. These non-lunar behaviors can create situations where the movement of fluids is not just governed by the direction of the flow, but is influenced by complex interactions within the fluid, such as swirling, rotating, and fluctuating velocities. For example, eddy currents can move in different directions than the overall flow. If a contaminant becomes caught in one of these eddies, it can be carried upstream or in a direction opposite to the current, despite the overall flow being downstream. This kind of movement can create a situation where the contaminant appears to defy the natural flow of the river, moving upstream or across the current. 2. The paradox. Contaminant flowing upstream. A. Eddy currents and localized flow reversal. The primary cause of the upstream contamination paradox lies in the behavior of eddy currents. When fluid flows through a pipe, river, or any other channel, the fluid doesn't always move uniformly. It may form localized areas where the fluid moves in a circular or spiral pattern. These localized currents are called eddies, and they can occur in turbulent flows, where the fluid's motion is chaotic. When a contaminant enters a turbulent flow, it can become entrained in one of these eddies. Depending on the nature of the vortex and the strength of the eddy current, the contaminant might be carried upstream. This is because the vortex's movement is independent of the main flow direction, meaning that the contaminant can be transported against the main direction of the river's current, creating a situation where the contaminant appears to be moving upstream. B. Low Reynolds number and microscale systems. The paradox becomes even more interesting in microscale systems, such as in microfluidics or very low Reynolds number flows. At very low Reynolds numbers, the flow is dominated by viscosity rather than inertia, and small, localized forces can move contaminants against the current with greater ease. This happens because the influence of turbulent eddies or other fluid instabilities is more pronounced at low Reynolds numbers, leading to more unpredictable and counterintuitive flow patterns. In small channels, where turbulence is minimal but fluid motion still creates localized circulation, contaminants can be sucked into eddies and move against the main flow. The result is that contaminants do not necessarily flow in the direction of the overall current, but instead follow complex trajectories dictated by the local fluid dynamics. 3. The role of boundary conditions in upstream contamination. A. The influence of riverbed topography. The behavior of contamination in a fluid is not solely determined by the flow velocity and eddy currents, but also by the geometry of the fluid channel. In a river, for example, the shape of the riverbed, such as bends, obstacles, or narrowing channels, can create conditions where upstream contamination becomes more likely. These factors affect the formation of vortices and the local mixing of the fluid. In areas where the river narrows or constricts, the water velocity increases, leading to the formation of more pronounced vortices that can draw contaminants against the main flow. Similarly, obstacles in the riverbed can disrupt the flow, creating areas of local circulation where contaminants can be trapped and carried upstream. B. Implications for pollution control. Understanding the dynamics of upstream contamination is critical for environmental science and pollution control. Traditional models of pollution in rivers assume that contaminants will spread downstream with the flow of the river. However, the paradox illustrates that nonlinear dynamics and turbulent mixing can lead to contaminants moving in unexpected directions. For pollution management, this means that upstream sources of contamination could have more widespread effects than initially assumed, as pollutants may travel in unpredictable directions based on local flow conditions. Therefore, monitoring systems must account for these complex dynamics to effectively track and manage the spread of contaminants. 4. Mathematical model of contaminant transport in nonlinear flows. A. Advection diffusion equation with eddy terms. To model contaminant transport in a system with eddy currents, we need to extend the traditional advection diffusion equation to account for the nonlinear behavior induced by turbulence and eddy currents. This can be done by introducing eddy diffusivity, or additional terms that represent the effect of nonlinear mixing in the fluid. The modified equation becomes Ct plus Uc equals GCTC plus Uc equals Gc, where Cc is the concentration of the contaminant, Uu is the velocity field of the flow, Gg is the eddy diffusivity term, which accounts for turbulent mixing, represents the spatial gradient. This equation accounts for the advection of the contaminant by the fluid, the diffusion of the contaminant due to molecular motion, and the effects of eddy currents or nonlinear mixing. In cases where eddy currents are strong enough, the system may exhibit behavior where contaminants move upstream or in unpredictable directions. Upstream contamination paradox. Imagine a river flowing downstream, and at some point, a contamination source is introduced into the water. Typically, we would expect the contamination to spread downstream with the flow of the water, traveling in the same direction. But here's the twist. In the upstream contamination paradox, this intuition is challenged. What if contamination could travel upstream, against the current, seemingly defying the natural flow of water? How can a contaminant travel against the very forces that are pushing everything downstream? This paradox arises from the complex dynamics of fluid systems, where the introduction of a contaminant in a flowing stream or river can lead to counterintuitive effects, particularly in systems with non-linear flows, eddy currents, or turbulent mixing. The paradox reveals how fluid dynamics, particularly in open channels like rivers or oceans, can lead to contamination behaving in ways that defy common assumptions about directionality and flow. Let's explore the upstream contamination paradox, where non-linear fluid dynamics and contaminant transport combine to create unexpected results in the movement of pollutants in natural systems. The upstream contamination paradox is not a specific thought experiment or principle directly named in the works of a prominent scientist, but rather a complex, counterintuitive phenomenon in fluid dynamics and environmental science. The paradox arises in the context of contaminant transport in natural water systems such as rivers, lakes, and oceans, where fluid flow and the spread of pollutants are studied. The paradox is rooted in the principles of fluid mechanics, advection diffusion, and non-linear dynamics, which describe how substances, including contaminants, are carried by the movement of fluid. In many classical fluid systems, we intuitively expect contaminants to follow the direction of flow, typically downstream or in the direction of the current. However, in natural systems, the turbulence and eddy currents present in rivers or oceans can create situations where contaminants move upstream or against the main direction of flow. This phenomenon is influenced by factors such as local mixing, fluid turbulence, and the boundary conditions of the riverbed or shoreline, which can create non-linear effects that reverse or complicate the expected flow. While the paradox has been studied in the context of pollution control and environmental science, it's also relevant in fields like hydrodynamics, meteorology, and engineering, where the behavior of fluid-transported substances needs to be understood. The upstream contamination paradox underscores the complexities of real-world fluid systems and serves as a reminder of how seemingly predictable systems can lead to unexpected outcomes. The upstream contamination paradox explores a scenario in which the behavior of contaminants in a flowing river or water system defies intuitive expectations. Normally, we assume that contaminants, when released into a fluid system, will be carried downstream with the flow. However, this paradox arises when contaminants seem to defy the direction of flow, traveling upstream or in the opposite direction of the flow. This paradox draws attention to the complexity of fluid dynamics, especially in systems with turbulence, eddies, and non-linear behavior. Let's break down the paradox, the mechanisms that lead to this counterintuitive behavior, and the mathematical framework that describes the transport of contaminants in fluid systems. 1. The basic concept of fluid flow and contaminant transport. A. Classical fluid flow. Advection and diffusion. In classical fluid dynamics, the transport of substances within a fluid is often described by the advection-diffusion equation, which combines two primary mechanisms. Advection, the movement of particles or contaminants with the fluid flow. In this case, the contaminant moves downstream with the flow of the river or water system. Diffusion, the spread of particles due to random motion, causing the contaminant to spread in all directions, even opposite to the direction of flow. The standard advection-diffusion equation in its simplest form is Ct plus Uc equals d2cx2 Tc plus ux2 equals dx22c, where C plus Cxt2 is the concentration of the contaminant at position xx and time tt. Uu is the velocity of the flow, dd is the diffusion coefficient, Cxxc represents the spatial gradient of the contaminant concentration, and 2cx2 x22c represents the diffusion term. In a simple scenario, advection would transport the contaminant downstream, while diffusion would cause the contaminant to spread, including in the upstream direction. However, Diffusion alone is not typically enough to carry the contaminant upstream unless specific conditions are met. B. Non-linear behavior in fluid systems. In real-world fluid systems like rivers or oceans, the flow is rarely smooth and linear. Instead, turbulence and eddies, vortices of fluid that rotate and move in circles, create non-linear dynamics in the fluid flow. These non-linear behaviors can create situations where the movement of fluids is not just governed by the direction of the flow, but is influenced by complex interactions within the fluid, such as swirling, rotating, and fluctuating velocities. For example, eddy currents can move in different directions than the overall flow. If a contaminant becomes caught in one of these eddies, it can be carried upstream or in a direction opposite to the current, despite the overall flow being downstream. This kind of movement can create a situation where the contaminant appears to defy the natural flow of the river, moving upstream or across the current. 2. The paradox. Contaminant flowing upstream, A, eddy currents and localized flow reversal. The primary cause of the upstream contamination paradox lies in the behavior of eddy currents. When fluid flows through a pipe, river, or any other channel, the fluid doesn't always move uniformly. It may form localized areas where the fluid moves in a circular or spiral pattern. These localized currents are called eddies, and they can occur in turbulent flows, where the fluid's motion is chaotic. When a contaminant enters a turbulent flow, it can become entrained in one of these eddies. Depending on the nature of the vortex and the strength of the eddy current, the contaminant might be carried upstream. This is because the vortex's movement is independent of the main flow direction, meaning that the contaminant can be transported against the main direction of the river's current, creating a situation where the contaminant appears to be moving upstream. B. Low Reynolds number and microscale systems. The paradox becomes even more interesting in microscale systems, such as in microfluidics or very low Reynolds number flows. At very low Reynolds numbers, the flow is dominated by viscosity rather than inertia, and small localized forces can move contaminants against the current with greater ease. This happens because the influence of turbulent eddies or other fluid instabilities is more pronounced at low Reynolds numbers, leading to more unpredictable and counterintuitive flow patterns. In small channels, where turbulence is minimal but fluid motion still creates localized circulation, contaminants can be sucked into eddies and move against the main flow. The result is that contaminants do not necessarily flow in the direction of the overall current, but instead follow complex trajectories dictated by the local fluid dynamics. 3. The role of boundary conditions in upstream contamination. A. The influence of riverbed topography. The behavior of contamination in a fluid is not solely determined by the flow velocity and eddy currents, but also by the geometry of the fluid channel. In a river, for example, the shape of the riverbed, such as bends, obstacles, or narrowing channels, can create conditions where upstream contamination becomes more likely. These factors affect the formation of vortices and the local mixing of the fluid. In areas where the river narrows or constricts, the water velocity increases, leading to the formation of more pronounced vortices that can draw contaminants against the main flow. Similarly, obstacles in the riverbed can disrupt the flow, creating areas of local circulation where contaminants can be trapped and carried upstream. B. Implications for pollution control. Understanding the dynamics of upstream contamination is critical for environmental science and pollution control. Traditional models of pollution in rivers assume that contaminants will spread downstream with the flow of the river. However, the paradox illustrates that non-linear dynamics and turbulent mixing can lead to contaminants moving in unexpected directions. For pollution management, this means that upstream sources of contamination could have more widespread effects than initially assumed, as pollutants may travel in unpredictable directions based on local flow conditions. Therefore, monitoring systems must account for these complex dynamics to effectively track and manage the spread of contaminants. 4. Mathematical model of contaminant transport in non-linear flows. A. The advection-diffusion equation with eddy terms. To model contaminant transport in a system with eddy currents, we need to extend the traditional advection-diffusion equation to account for the non-linear behavior induced by turbulence and eddy currents. This can be done by introducing eddy diffusivity or additional terms that represent the effect of non-linear mixing in the fluid. The modified equation becomes Ct plus UCC equals GCT plus UC equals GCT, where Cc is the concentration of the contaminant, UU is the velocity field of the flow, Gg is the eddy diffusivity term, which accounts for turbulent mixing, represents the spatial gradient. This equation accounts for the advection of the contaminant by the fluid, the diffusion of the contaminant due to molecular motion, and the effects of eddy currents or nonlinear mixing. In cases where eddy currents are strong enough, the system may exhibit behavior where contaminants move upstream or in unpredictable directions. Bentley's paradox. Imagine a small object moving through a fluid in a narrow tube. As the fluid flows, you might expect the object to encounter some resistance, particularly from the viscosity of the fluid. Now, let's make things even more interesting. What happens if the tube has a sudden bend or change in geometry? In Bentley's paradox, this seemingly simple setup leads to a surprising result. When fluid flows through a pipe with a sharp bend or sudden change in geometry, the object's motion and resistance don't behave in the way we'd expect. In fact, the paradox reveals that under certain conditions, the fluid flow at the bend can lead to non-linear effects, where the expected resistance doesn't arise or even becomes unpredictable. The paradox, introduced by Bentley, challenges the way we think about viscosity and fluid dynamics, particularly in confined spaces and pipes. How do changes in geometry affect the flow of fluids, and why does this lead to seemingly counterintuitive behavior? Let's explore Bentley's paradox, where fluid geometry and non-linear effects converge in a surprising way, reshaping our understanding of resistance and flow in confined spaces. Bentley's paradox is a phenomenon explored in the study of fluid dynamics, particularly focusing on the effects of geometry on flow behavior and resistance. While the paradox does not have a direct historical connection to one specific scientific figure or seminal paper, it has been discussed in the context of fluid mechanics, where understanding the way fluid flows in pipes and channels is essential for various engineering applications. Bentley, an early contributor to the field of hydrodynamics, pointed out an interesting and counterintuitive aspect of fluid flow through bends and irregular geometries. The paradox arises when we examine how sharp bends or sudden changes in the geometry of pipes and channels influence the resistance experienced by objects or fluids traveling through them. Traditional fluid dynamics suggests that viscosity should lead to increased resistance as the fluid moves through a pipe or tube. However, Bentley's exploration showed that under certain conditions, particularly when sharp bends or turbulent flows are involved, the expected resistance does not manifest in the typical way. Bentley's paradox is a key thought experiment in nonlinear fluid dynamics, revealing how fluid behavior can become complex in real-world systems, where things like pipe geometry, turbulence and viscosity interact in unexpected ways. The paradox highlights the need for further understanding of fluid resistance in confined spaces and has implications for the design of fluid transport systems such as pipes, tubes, and channels in engineering. The Bentley's paradox explores an interesting and non-intuitive situation in fluid dynamics, where sharp bends or sudden changes in geometry of pipes and fluid channels lead to unexpected effects in the way fluid resistance behaves. The paradox challenges our usual understanding of viscous drag and fluid flow through confined spaces by illustrating that the geometry of the flow can significantly alter the behavior of the fluid and the resistance experienced by objects moving through it. 1. The basics of fluid flow and viscosity. A. Viscosity and resistance. Viscosity is a measure of a fluid's resistance to flow. It describes the internal friction between the fluid layers as they slide past one another. In a low viscosity fluid like water, the resistance to flow is relatively small. However, in a high viscosity fluid such as honey, there is more resistance to flow. Viscosity is a key factor in hydrodynamic resistance, which dictates how difficult it is for an object to move through a fluid. Where sharp bends or sudden changes in geometry of pipes and fluid channels lead to unexpected effects in the way fluid resistance behaves, the paradox challenges our usual understanding of viscous drag and fluid flow through confined spaces by illustrating that the geometry of the flow can significantly alter the behavior of the fluid and the resistance experienced by objects moving through it. 1. The basics of fluid flow and viscosity. A. Viscosity and resistance. Viscosity is a measure of a fluid's resistance to flow. It describes the internal friction between the fluid layers as they slide past one another. In a low viscosity fluid like water, the resistance to flow is relatively small. However, in a high viscosity fluid such as honey, there is more resistance to flow. Viscosity is a key factor in hydrodynamic resistance, which dictates how difficult it is for an object to move through a fluid. When an object moves through a fluid, it experiences a drag force due to the viscous forces acting on it. The drag force, Fd, on a sphere moving through a fluid can be calculated using Stokes' law for low Reynolds numbers, which is given by Fd equals 6, RVF equals 6 perv, where E is the viscosity of the fluid, R is the radius of the object, VV is the velocity of the object. At first glance, the relationship between viscosity and drag is straightforward. Higher viscosity leads to higher resistance. But Bentley's paradox shows that when fluid flows through channels with sharp bends or changes in geometry, the expected resistance is altered due to the complex flow patterns that form. B. The role of pipe geometry in fluid flow. When fluid flows through a pipe or channel, the geometry of the pipe plays a significant role in determining the resistance experienced by the fluid. The length, diameter, and shape of the pipe influence the flow characteristics, especially in confined spaces. As fluid moves through a pipe, the velocity profile typically shows that the fluid near the edges of the pipe moves slower than the fluid in the center, due to friction with the pipe walls. This creates a boundary layer near the edges of the pipe, where the velocity changes gradually. The typical understanding is that larger pipes have lower resistance because they allow more fluid to flow through them with less friction. However, when there are sudden bends or sharp changes in the geometry, such as elbows or constrictions, the flow can become more complex, leading to unexpected changes in the drag and resistance experienced by an object in the fluid. 2. The paradox. Resistance in curved or narrowed pipelines. A. Flow through curved sections. Bentley's paradox specifically focuses on sharp bends or sudden changes in geometry in pipes. In the idealized case of fluid flow through a straight pipe, the flow is expected to be smooth and predictable. As the fluid moves through the pipe, it experiences a drag force that slows down the motion of any object within the fluid. However, when the pipe bends sharply, the flow patterns become disrupted. The fluid in the curved section of the pipe is forced to change direction, creating eddies and turbulent flow. This change in flow direction introduces non-linear dynamics to the system, which can lead to unexpected behavior in terms of drag and resistance. In some cases, instead of increasing the resistance, as we would expect in a conventional, straight pipe, the sharp bend or constriction may reduce the effective drag on an object. This can happen because the centrifugal force created by the bend might induce turbulent eddies that interact with the object in such a way that the object faces less drag than it would in a straight pipe. The paradox arises when higher viscosity and nonlinear flow combine to create a situation where resistance is not directly proportional to the viscosity or size of the pipe, as we might assume from classical fluid dynamics. B. Sudden constrictions and expansions. In addition to sharp bends, sudden constrictions or expansions in the geometry of the pipe can lead to nonlinear effects that alter the flow characteristics. When the fluid flows through a narrow section, the velocity increases due to the continuity equation, the conservation of mass, which dictates that if the cross-sectional area of the pipe decreases, the fluid velocity must increase to maintain the same flow rate. This change in velocity leads to a pressure drop across the constriction. However, when the pipe expands again, the velocity decreases and the pressure increases. These changes in pressure and velocity can cause flow separation or the formation of turbulent eddies, which affect how the fluid behaves as it moves through the system. The paradox comes into play because, in certain configurations, the viscosity of the fluid may not behave in the way we expect. In regions where the flow becomes turbulent or where eddy currents form, the drag force on an object can be reduced, and the system's resistance might not increase as we would assume from classic fluid theory. 3. The mathematical model of fluid resistance in complex geometries. A. The Navier-Stokes equations and nonlinear flow. The behavior of fluid flow through a pipe with bends and constrictions can be modeled using the Navier-Stokes equations, which govern the motion of viscous fluids. These equations are highly nonlinear, meaning that small changes in the velocity pressure, or geometry of the system can lead to large unpredictable effects on the flow. The Navier-Stokes equations for an incompressible viscous fluid are ut plus uu equals 1p plus 2u plus ftu plus u equals minus r1p plus n2u plus f, where uu is the velocity vector of the fluid, pp is the pressure, n is the kinematic viscosity, r is the density of the fluid, ff represents external forces acting on the fluid, such as gravity. In regions where the fluid flows through bends or narrowed sections, the velocity gradient and pressure distribution become complex. The resulting turbulent flow can lead to non-linear drag effects, creating situations where the expected resistance is not observed. 4. Real-world applications of Bentley's paradox. A. Hydraulic systems and pipe networks. Bentley's paradox has practical applications in the design of hydraulic systems and pipe networks. Engineers designing systems that transport fluids through pipes must account for the effects of geometry on fluid flow, particularly in systems with curved sections or sudden constrictions. The paradox highlights the need to understand how turbulent flow and nonlinear dynamics can influence the performance of such systems, especially when calculating energy losses or designing systems for efficient fluid transport. B. Pollution control and fluid transport. In pollution control and fluid transport, the paradox is relevant when considering how pollutants or fluids move through confined channels. Understanding how contaminants interact with non-linear fluid dynamics helps in designing efficient filtration and transport systems. The paradox also informs the design of chemical reactors, wastewater treatment plants, and oil pipelines, where understanding flow behavior in complex geometries is critical. B. The multiverse and infinite universes. The paradox also has implications for the multiverse theory, which suggests that our universe is just one of many in a vast multiverse. In an infinite multiverse, each universe could have different physical laws, and the probability of Boltzmann brains arising in one of these universes may be much higher than in a finite system. This raises the possibility that random consciousnesses may be a common feature of infinite multiverse systems, further complicating the notion of a coherent and objective reality. Boltzmann brain paradox. Imagine that you are a conscious being, aware of your surroundings, your thoughts, and your existence. But now, what if I told you that your existence might be nothing more than a temporary fluctuation in the universe's chaotic behavior? What if you were simply a Boltzmann brain, a spontaneous and fleeting consciousness that arises from the random motion of particles in an otherwise entropic universe? The Boltzmann brain paradox explores this unsettling idea, suggesting that in a universe governed by entropy and random fluctuations, the probability of a single brain forming out of pure chaos could be just as high as the probability of the entire universe we observe. According to the paradox, in the far future, or even within certain models of the universe, the spontaneous formation of a conscious brain could occur due to sheer randomness, raising deep questions about reality, consciousness, and the nature of the universe. If the universe is vast and entropic enough, could we all be nothing more than temporary brains floating in a sea of cosmic chaos? Let's dive into the Boltzmann brain paradox, where entropy, probability, and consciousness converge in a mind-bending scenario that challenges the way we think about our place in the universe. The Boltzmann brain paradox is named after the famous Austrian physicist Ludwig Boltzmann, who is best known for his work in statistical mechanics and the study of entropy in thermodynamic systems. Boltzmann's statistical approach helped explain the microscopic behavior of particles and how they give rise to the macroscopic properties of gases, liquids, and solids. Central to his work was the idea of entropy, the tendency for systems to move toward disorder and randomness. In the 19th century, Boltzmann proposed that, given enough time, the universe would naturally evolve toward a state of maximum entropy. Over immense periods of time, it seemed probable that, in a universe driven by the second law of thermodynamics, random fluctuations might create unlikely events, such as the spontaneous appearance of molecules or even organisms. The Boltzmann brain concept arose from this idea, suggesting that in an infinite universe, it would be statistically possible for a self-aware brain to spontaneously emerge due to the chaotic arrangement of particles. In modern cosmology, the Boltzmann brain paradox has sparked a deep philosophical debate about probability, consciousness, and the nature of reality. The paradox suggests that in an eternally fluctuating universe, the random formation of a brain, complete with memories and a sense of self, might be more likely than the formation of a coherent universe like the one we observe. The paradox raises uncomfortable questions about the likelihood of our existence and whether we can trust our experiences as real. The Boltzmann brain paradox introduces a deeply unsettling idea about the nature of consciousness and the probability of our existence in an entropic universe. At its core, the paradox challenges our understanding of reality, suggesting that it might be more probable for a random fluctuation to create a conscious being, a Boltzmann brain, than for the entire universe to evolve as it has. To unpack this paradox, we need to explore the concepts of entropy, statistical mechanics, and probability in the context of an infinite universe. 1. Entropy and the second law of thermodynamics. A. The concept of entropy. Entropy is a fundamental concept in thermodynamics that measures the degree of disorder or randomness in a system. It is a measure of how much energy in a system has become unavailable for work due to its disordered state. The second law of thermodynamics states that the entropy of an isolated system will tend to increase over time, meaning that systems naturally move toward a state of maximum disorder or equilibrium. In the context of the universe, this implies that the universe as a whole is moving toward a state of heat death, a state in which all energy is evenly distributed and no more work can be performed. The universe's future will be one of maximum entropy, where no life or organized structures can exist. B. Entropy and statistical mechanics. Boltzmann's work in statistical mechanics focused on how the microscopic behavior of particles gives rise to the macroscopic thermodynamic properties of materials. He demonstrated that the randomness and disorganization at the particle level lead to observable phenomena like pressure, temperature, and volume in gases. Boltzmann also proposed that the universe could be considered a statistical system, a system where the future state of the universe depends on the statistical arrangement of its particles. In an entropic universe, particles are constantly in motion, and the arrangement of these particles leads to higher entropy over time. However, due to the infinite possibilities for the arrangement of particles, unlikely fluctuations, such as the sudden formation of highly ordered structures like conscious beings, become possible over vast timescales. 2. The formation of a Boltzmann brain. A. The statistical probability of a brain. The idea behind the Boltzmann brain is rooted in the concept that, given an infinite amount of time, random fluctuations in the universe could lead to the formation of highly ordered systems. The paradox arises when we apply this idea to the formation of consciousness. In an infinite universe, statistical mechanics suggest that eventually, a random fluctuation could cause particles to arrange themselves into a self-aware brain, complete with memories and a sense of self. A Boltzmann brain would be a temporary random fluctuation that appears for a brief moment in time, only to dissipate back into chaos. The brain would not necessarily be connected to any larger coherent system like the universe as we know it, but would be a short-lived, isolated consciousness, essentially a fleeting and random instance of self-awareness. B. Why the brain is more likely than the universe? The paradox arises when we consider the probability of a Boltzmann brain compared to the probability of a coherent universe like the one we observe. The paradox arises when we apply this idea to the formation of consciousness. In an infinite universe, statistical mechanics suggest that eventually, a random fluctuation could cause particles to arrange themselves into a self-aware brain, complete with memories and a sense of self. A Boltzmann brain would be a temporary random fluctuation that appears for a brief moment in time, only to dissipate back into chaos. The brain would not necessarily be connected to any larger coherent system like the universe as we know it, but would be a short-lived, isolated consciousness, essentially a fleeting and random instance of self-awareness. B. Why the brain is more likely than the universe? The paradox arises when we consider the probability of a Boltzmann brain compared to to the probability of a coherent universe like the one we observe. In a universe governed by entropy, the likelihood of the entire universe spontaneously organizing itself into complex, ordered systems, like galaxies, planets, and life forms, seems extremely low compared to the probability of a single brain forming out of random fluctuations. Since the Boltzmann brain arises from a random fluctuation, the number of possible configurations that lead to the formation of a brain is so much greater than the configurations needed to form an entire universe that statistically a brain could form much more easily. The universe in this context is just a rare complex configuration in an entropic system, and the brain, as a much simpler configuration, is much more probable. This creates an unsettling scenario. If the universe is infinite and governed by entropy, it might be more likely that we are all Boltzmann brains, isolated temporary consciousnesses that arise randomly in an otherwise chaotic universe, than that we are part of a coherent, well-ordered universe with a consistent history. 3. The paradox of our consciousness and the nature of reality. A. Philosophical implications for reality. The Boltzmann brain paradox raises profound philosophical questions about the nature of consciousness and reality. If it is more likely that we are Boltzmann brains than part of a real, consistent universe, this casts doubt on our perception of reality. The paradox forces us to confront the idea that what we experience as the universe could be nothing more than a fleeting and random occurrence, a brief fluctuation in the grand scheme of an entropic cosmos. This brings up the question, how can we trust our own perceptions of reality? If we are Boltzmann brains, there may be no external reality at all, only our internal, self-generated experience of the world. This challenges the very idea of objective reality, suggesting that our perception of the universe could be the result of a random fluctuation in an entropic system, disconnected from any larger structure or purpose. B. The problem of infinite time and probability. The paradox also raises concerns about infinite time and the probability of events occurring in an eternal universe. The idea that random fluctuations could lead to spontaneous brains forming from nothing creates a tension between the probabilistic nature of the universe and our expectation of coherent, predictable events. If there is enough time and enough possible configurations for random events to occur, the universe may be filled with an infinite number of Boltzmann brains, each with a unique perception of reality, but none of them truly connected to any external universe. C. Resolving the paradox. One way to resolve the Boltzmann brain paradox is to recognize that while the formation of a Boltzmann brain is statistically possible in an infinite universe, it is still highly unlikely. The universe, as we observe it, may be a much rarer and more stable configuration than a single, randomly fluctuating brain. In this sense, we can argue that, although Boltzmann brains are theoretically possible, they are not likely to be the origin of our existence or consciousness. 4. Implications for cosmology and the universe's future. A. The heat death of the universe. The Boltzmann brain paradox is intricately connected to the heat death of the universe. As the universe continues to expand and approach a state of maximum entropy, the probability of ordered systems forming decreases over time. In this future, the universe will be dominated by random fluctuations and isolated events, where Boltzmann brains could emerge from the chaotic environment. Fermi paradox. The universe is vast, so vast that it seems almost impossible for us to be the only intelligent life in existence. With billions of stars in our galaxy alone, many of them with planets in the habitable zone, the probability of other civilizations existing somewhere in the cosmos seems incredibly high. And yet, we've heard nothing. No signals, no visits, no evidence of advanced civilizations reaching out to us. This is the essence of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of evidence for or contact with such civilizations. Why, given the vastness of the universe and the potential for life to evolve on other planets, haven't we made contact with any alien species? Why haven't we detected any signs of intelligent life in the cosmos? The paradox was famously raised by Enrico Fermi during a casual conversation in the 1950s, and it continues to haunt our search for extraterrestrial intelligence. SETI. Let's explore the Fermi paradox, where the size of the universe and the silence of space seem to suggest an unsettling mystery about our place in the cosmos. The Fermi paradox was famously articulated by physicist Enrico Fermi in the 1950s. Fermi, along with his colleagues at the Los Alamos National Laboratory, was having a casual conversation about the possibility of extraterrestrial life when he posed the now famous question, where is everybody? Despite the immense size of the universe and the seemingly high probability of other intelligent civilizations existing, there was no evidence to suggest that alien life had reached out or made contact with us. Fermi's question has since become a central puzzle in the search for extraterrestrial intelligence, SETI, and remains one of the most enduring and perplexing paradoxes in science. The paradox arises from the Drake equation, a mathematical framework developed in the 1960s by astrophysicist Frank Drake. The equation attempts to estimate the number of technologically advanced civilizations in our galaxy based on factors like the number of stars, the likelihood of planets forming, and the probability of those planets hosting life. According to the equation, the universe should be teeming with alien civilizations. Yet, despite decades of searching, we have found no direct evidence of extraterrestrial life, or any signals that would suggest such civilizations exist. The Fermi paradox has led to numerous theories and explanations, ranging from the possibility that alien civilizations are too far away or too different to detect, to the unsettling possibility that intelligent civilizations self-destruct before they can make contact. The paradox continues to fuel scientific inquiry, philosophical debate, and the ongoing search for life beyond Earth. The Fermi paradox highlights the striking inconsistency between the high probability of extraterrestrial life and the complete absence of evidence for it. Despite the universe's vast size and age, and the likelihood of many habitable planets, we have not made contact with any alien civilizations. To unpack the paradox, we need to explore the factors that contribute to the high probability of extraterrestrial life and the lack of evidence that contradicts that probability. 1. The high probability of extraterrestrial life. A. The size of the universe. The most compelling argument for the existence of extraterrestrial life comes from the sheer size of the universe. Our galaxy, the Milky Way, contains approximately 100 to 400 billion stars, many of which have planets orbiting them. Recent discoveries suggest that exoplanets, planets outside our solar system, are common, and many of these planets lie in the habitable zone of their stars, where conditions could allow for liquid water to exist. With the discovery of thousands of exoplanets, it seems statistically likely that some of these planets harbour conditions conducive to life. Moreover, our galaxy is just one of over 100 billion galaxies in the observable universe. This vast number of stars and planets means that the chances of life arising elsewhere in the universe are incredibly high. Given the number of planets that could support life, the probability of intelligent life developing on at least a few of them seems almost certain. B. The Drake equation. The Drake equation is a mathematical formula designed to estimate the number of technologically advanced civilizations in the galaxy. The equation takes into account factors such as the rate of star formation, the fraction of stars with planets, the number of planets that can potentially support life, the fraction of those planets that develop life, the fraction of civilizations that develop technology capable of communication, the lifespan of technologically advanced civilizations. The equation suggests that, given the vast number of stars and planets in the Milky Way, the number of civilizations that could communicate with us should be significant. Even with conservative estimates, the number of potential extraterrestrial civilizations should be high enough that we should have already detected some signal or evidence of their existence. C. The probability of life evolving life on Earth evolved relatively quickly, emerging within 1 billion years of the planet's formation. This rapid emergence of life suggests that, under the right conditions, life might be a common outcome on suitable planets. In fact, some scientists argue that life is likely to emerge almost whenever conditions are favourable, making it even more probable that intelligent life exists elsewhere. Given the immense number of potentially habitable planets and the relatively quick evolution of life, it stands to reason that life, possibly even intelligent life, exists elsewhere in the universe. Yet, despite these high probabilities, we have no direct evidence of extraterrestrial intelligence. 2. The lack of evidence for extraterrestrial life. A. The Fermi paradox. Where is everybody? Given the vastness of the universe and the high probability of life elsewhere, the paradox arises. Why haven't we found any evidence of extraterrestrial civilizations? The most direct way we might expect to detect extraterrestrial life is through the detection of radio signals or other electromagnetic emissions from distant civilizations. The search for extraterrestrial intelligence, SETI, has been ongoing for decades, yet we have not detected any signals that could be attributed to an intelligent civilization. In Fermi's words, where is everybody? Given the vast number of potential civilizations in our galaxy, the silence is deafening. The paradox becomes even more perplexing when we consider the potential longevity of these civilizations. If advanced civilizations have existed for millions of years, they should have had ample time to send signals, explore the galaxy, or even colonize nearby star systems, and yet there is no sign of them. B. The Great Silence. Possible explanations. Several explanations have been proposed for the lack of evidence of extraterrestrial life. These range from the technological limitations of our current detection methods to more speculative ideas about the nature of alien civilizations. Technological limitations. One explanation is that our current technology is simply not advanced enough to detect the signals or activities of extraterrestrial civilizations. Our radio telescopes are sensitive only to a narrow range of frequencies, and we may be missing signals that fall outside of our detection range. The rare Earth hypothesis. This hypothesis posits that while there may be many planets that could support life, the specific conditions required for complex life to emerge are extremely rare. Factors such as the planet's location in the habitable zone, the presence of a large moon, a magnetic field, and the right chemical composition may be so rare that intelligent life is an anomaly. The Great Filter. Another theory suggests that advanced civilizations may have a tendency to self-destruct before they can make contact. The idea is that there might be a great filter, a stage in the development of intelligent life that is extremely difficult to pass. This could be the result of nuclear war, ecological collapse, or other existential threats. If this is the case, the silence may be a sign that intelligent civilizations often destroy themselves before they can communicate or explore the galaxy. Zoo hypothesis. The zoo hypothesis suggests that extraterrestrial civilizations are aware of us, but deliberately avoid making contact. This could be because they wish to observe us without interfering with our development, much like humans observe animals in a zoo. This scenario raises questions about the ethics and motivations of advanced civilizations. C. The dark forest hypothesis. The dark forest hypothesis is another speculative explanation for the Fermi paradox. According to this hypothesis, advanced civilizations may be deliberately silent because they see other civilizations as potential threats. In a universe where resources are limited and survival is paramount, civilizations might stay hidden to avoid detection by others. Just as a hunter in a dark forest might be cautious not to reveal their position, extraterrestrial civilizations might be cautious not to reveal their existence to others. This idea suggests that the reason for the Great Silence could be a cosmic survival strategy, where advanced civilizations avoid broadcasting their presence to protect themselves. 3. Possible solutions to the Fermi paradox. A. We are not listening on the right channels. One possible solution to the Fermi paradox is that we are simply not listening on the right frequencies or using the right methods to detect extraterrestrial signals. It's possible that alien civilizations use forms of communication that are entirely different from our own, such as optical communication, laser pulses, or even quantum entanglement. As our technology advances, we may uncover new ways to detect signals from alien civilizations. B. The role of distance and time. Another possible solution is that the vast distances between stars make interstellar communication or travel incredibly difficult. Even if alien civilizations exist, they might be too far away to detect or communicate with us. Additionally, the universe is billions of years old, and civilizations might rise and fall over time. We might just be too early in the history of the universe to make contact with another civilization that is at a similar level of technological advancement. C. We are alone, finally. One of the more unsettling possibilities is that we are truly alone in the universe. Perhaps the conditions required for the emergence of intelligent life are so rare that we are the only ones who have developed consciousness and technology. In this case, the Fermi paradox would simply be a consequence of the unique nature of our existence. Heat-death paradox. The universe is vast, filled with galaxies, stars and planets, but what happens when all of that energy and motion eventually runs out? Imagine a future where everything has cooled, all stars have burned out, and there is no more activity left in the cosmos. This is the concept of heat death, a state where the universe has reached maximum entropy and all energy is uniformly spread out. But here's the paradox. If the universe reaches heat death, then nothing can happen anymore. There will be no motion, no change, and no life. Yet, the very notion of entropy and thermodynamics suggests that this end state is inevitable. How can the universe, which is constantly evolving, ever come to a point where nothing can change, where all processes cease? The heat-death paradox raises questions about the future of the universe, the ultimate fate of everything we know, and the apparent contradiction between the universe's ever-expanding potential and its eventual thermodynamic equilibrium. Let's explore this paradox where the end of time and the cooling of the cosmos challenge our understanding of change, life, and the very nature of existence. The concept of heat death originates from thermodynamics and the study of entropy, particularly through the work of physicists like Ludwig Boltzmann and Rudolf Clausius. The idea comes from the second law of thermodynamics, which states that in any closed system, entropy, a measure of disorder, will tend to increase over time. As systems move toward higher entropy, the ability to do useful work diminishes, and eventually, all energy in a system becomes uniformly distributed, leading to a state of no usable energy. James Clerk Maxwell and Lord Kelvin contributed to the early ideas of heat death by theorizing that the universe would eventually run out of usable energy as stars burn through their fuel and galaxies drift apart. This idea was further developed in the 19th and 20th centuries as our understanding of cosmology and the Big Bang theory advanced. Max Planck and Albert Einstein later expanded on thermodynamic ideas by introducing the concepts of quantum mechanics and general relativity, which also suggested that the universe's eventual fate might be a state of equilibrium, where no significant changes could occur. The heat-death paradox has been a topic of philosophical and scientific discussion, especially in the context of cosmology and the future of the universe. While it remains a cornerstone of our understanding of thermodynamic equilibrium, the paradox raises fundamental questions about time, existence, and whether a state of absolute stasis can truly be the end of everything. The heat-death paradox represents the theoretical end of the universe, when all matter and energy are uniformly distributed and no work or processes can take place. This paradox is based on the second law of thermodynamics, which implies that the universe's entropy will increase until everything is in a state of maximum disorder. While this idea seems inevitable given the laws of physics, it presents a paradox. If the universe reaches heat death, everything would come to a standstill. How can the universe, which is defined by motion, change, and dynamism, reach a state where absolutely nothing happens? 1. The second law of thermodynamics and entropy. A. The basics of entropy. The second law of thermodynamics states that the entropy of an isolated system always increases over time. Entropy is a measure of disorder or randomness. In simple terms, it represents how much energy in a system is unavailable to do useful work. As entropy increases, systems naturally progress toward a state where the energy is evenly spread out and no further useful work can be extracted from it. For example, consider a hot cup of coffee sitting in a cool room. Over time, the heat from the coffee will dissipate into the surrounding air, causing both the coffee and the air to reach thermal equilibrium. The heat is no longer concentrated in one area, and the system has moved toward a state of maximum entropy. Everything is in a uniform state, and no more useful work can be done. In the context of the universe, the idea is that over a long enough timescale, everything will eventually spread out and equalize. Stars will burn through their fuel and eventually extinguish, galaxies will drift apart, and all matter will be evenly distributed. As a result, the universe will reach a point where there is no energy gradient left to fuel any process. This is the heat death. B. The role of heat death in thermodynamics. Heat death refers to a state of the universe where maximum entropy has been reached, meaning that all the energy is evenly spread out across space. In this state, no physical processes can occur, because all energy is uniformly distributed, and there are no temperature gradients or chemical reactions to drive change. In essence, the universe would be in a state of thermal equilibrium, where all activity ceases. If the universe reaches this point, there would be no motion, no life, no stars, just a cold, uniform expanse of energy that is incapable of doing work. This scenario represents the ultimate end of time, where the universe is in perfect stasis, unable to evolve or change. 2. The paradox. Can the universe reach stasis? A. Motion and change in the universe. At the heart of the heat-death paradox is the question of motion and change. The universe as we know it is characterized by motion, the movement of galaxies, the birth and death of stars, the formation of planets and the evolution of life. Change, both at the cosmic scale and the human scale, is fundamental to our understanding of reality. Yet, if the universe were to reach heat-death, it would represent the end of all motion. There would be no more changes or events, just an unchanging stagnant state. This creates a paradox, because time itself is defined by the passage of events. If nothing changes, how can time continue? How can we reconcile the universe's inherent dynamism with the idea of a timeless static end? B. The passage of time. The passage of time is deeply tied to the thermodynamic flow. We experience time through the unfolding of events and processes. As entropy increases, processes like the expansion of the universe, the cooling of stars, and the diffusion of energy naturally progress. However, if the universe reaches maximum entropy and everything reaches a uniform state, time would seemingly come to an end. Without change, there would be no way to distinguish between past and future, and time as we understand it would cease to have any meaning. This paradox brings us face to face with the concept of irreversibility. The second law of thermodynamics dictates that processes move in one direction, toward increasing entropy. The question, however, is whether the universe's final state, heat-death, represents the end of time itself. 3. The mathematical underpinnings of heat-death. A. Entropy and cosmological evolution. To understand heat-death more formally, we must examine its implications for the cosmological evolution of the universe. The Big Bang marks the universe's initial state, which was highly ordered, with energy and matter concentrated in a single, incredibly hot point. As the universe expanded, entropy began to increase as energy spread out and systems became more disordered. This cosmic expansion is governed by the Friedmann equations, which describe the expansion of space and the distribution of energy within the universe. Over time, the universe's energy density decreases, and the process of entropy increase accelerates. As galaxies move farther apart and stars burn out, the universe enters a phase where no new energy is being generated. Ultimately, the universe will reach a point where it has reached thermal equilibrium, with no more available energy for processes like star formation or life. B. The Boltzmann distribution and the fate of energy. The Boltzmann distribution is a statistical description of how particles in a system distribute energy at different temperatures. It plays a key role in explaining why energy tends to spread out evenly over time. In the universe, energy will eventually reach a state where the energy of every particle is uniformly distributed, and all processes requiring energy will stop. This is the mathematical basis for the heat-death scenario. The energy distribution will reach a point where there is no usable concentration of energy. Everything will be spread out, and the temperature of the universe will approach absolute zero, effectively halting all processes. In this state, the universe will be lifeless, with no stars or galaxies, and no way to extract usable energy from the environment. 4. The heat-death paradox and its philosophical implications. A. The nature of time and change. One of the profound philosophical implications of the heat-death paradox is the concept of time itself. If the universe reaches a state of absolute entropy, where no processes can occur, does time itself become irrelevant? Time, as we perceive it, is tied to events and change. If the universe becomes a cold, uniform expanse, without any change, does time have meaning? This paradox challenges the fundamental nature of time as a constant flowing entity. B. The end of the universe and the meaning of existence. The idea of heat-death raises existential questions about the meaning and purpose of life and the universe. If all systems inevitably succumb to entropy and eventually reach a state of uniformity, does the universe have any ultimate purpose? Is the universe's expansion, the formation of stars, and the evolution of life merely a temporary phase in the inevitable march towards stasis? Some philosophers and cosmologists argue that the concept of heat-death underscores the temporary nature of everything in the universe, including life itself. This might lead to a reflection on human existence and our place in the larger cosmic picture. Bootstrap Paradox. Imagine a magnet moving through a loop of wire. We know from Faraday's law of induction that a moving magnet will induce a current in the wire. But here's the twist. What if the magnet is moving in a way that seems to contradict everything we know about electromagnetic induction? The Faraday paradox arises in a seemingly straightforward situation involving magnetic fields, induced currents, and relative motion. In this paradox, the direction of the induced current appears to depend on the frame of reference and the way we analyze the motion of the magnet. To make matters even more puzzling, the paradox raises the question: does motion in one reference frame lead to different results compared to motion in another frame, even if the physical laws remain the same? The Faraday paradox brings to the forefront the fascinating relationship between magnetic fields, electric currents, and the concept of relative motion. It challenges our understanding of induction and provides a deep dive into the nature of electromagnetic interactions in a world defined by both electric and magnetic forces. Let's explore the Faraday paradox, where motion, magnetic induction, and electromagnetic theory collide in an unexpected and mind-bending way. The Faraday paradox is rooted in the fundamental principles of electromagnetism, particularly the concepts of electromagnetic induction, first discovered by Michael Faraday in the early 19th century. Faraday's work laid the foundation for our understanding of how magnetic fields can induce electric currents in conductors, a phenomenon encapsulated in Faraday's law of induction. Faraday's law states that a time-varying magnetic field, either by movement or changing strength, will induce an electromotive force, EMF, which drives an electric current in a nearby conductor. While Faraday's discoveries were groundbreaking, they also led to some paradoxical situations that question the relationship between magnetic fields, electric currents, and reference frames. The Faraday paradox arose from a thought experiment involving the motion of a magnet relative to a loop of wire. The paradox emerged from the idea that the induced current in the wire seemed to depend on the reference frame of the observer, even though the physical situation appeared the same in any inertial frame. This paradox challenges our understanding of electromagnetic induction and relative motion, particularly in the context of how magnetic fields and electric fields interact. It poses a fundamental question about the relationship between space, motion, and electromagnetic forces, and it serves as a point of deep reflection for scientists in fields like electromagnetic theory, special relativity, and classical mechanics. The Faraday paradox challenges the very foundation of electromagnetic theory by raising questions about how motion and relative reference frames affect the behavior of induced currents. While Faraday's law of induction tells us that a changing magnetic field induces an electric current, the paradox highlights situations where this law seems to produce different results based on the observer's perspective. To fully understand the paradox, we need to delve into the relationship between magnetic fields, electric currents, motion, and the frame of reference from which the system is observed. 1. Faraday's law of induction and the basics of electromagnetic induction. Faraday's law of induction. Faraday's law describes how a magnetic field can induce an electric current in a conductor. The law states that the induced electromotive force, EMF, in a closed loop is proportional to the rate of change of the magnetic flux through the loop. Mathematically, this law is expressed as E equals D, P height, dPHB, D2, where E is the electromotive force, EMF, induced in the loop. P height is the magnetic flux through the loop. T is time. The magnetic flux, PHB, is given by the product of the magnetic field B and the area of the loop, and the induced current arises when the magnetic flux is changing with time. When a magnet moves through a conductor, or when the conductor moves through a magnetic field, the changing magnetic flux induces a current in the conductor, which is the basis for the operation of devices like generators and transformers. Magnetic fields and electric currents. The key idea behind Faraday's law is that motion relative to a magnetic field produces an induced current. This happens because the magnetic field lines passing through the conductor change as the magnet moves or as the field strength fluctuates. This change in flux creates an electric field, which drives the current through the conductor. The direction of the induced current is determined by Lenz's law, which states that the current will flow in such a way as to oppose the change in flux that caused it. For instance, if the magnetic field through the loop increases, the induced current will flow in a direction that produces a magnetic field to counteract the increase. 2. The Faraday paradox. Induced currents and reference frames. The thought experiment. The Faraday paradox arises when we consider the scenario where a magnet is moving through a loop of wire, and we analyze the situation from different reference frames. Suppose we have a stationary loop and a magnet moving through it. According to Faraday's law, the movement of the magnet will induce an electric current in the loop because the magnetic flux through the loop changes as the magnet moves. However, if we switch to a reference frame in which the magnet is stationary and the loop is moving, the situation should be equivalent in terms of the magnetic flux. But in this new frame, the current should still be induced, except the reason would now be that the loop is cutting through the magnetic field lines rather than the magnet moving. This raises the question, why does the induced current depend on the reference frame? The Faraday paradox arises because the two situations, magnet moving versus loop moving, seem to produce different answers about how the induced current behaves. According to special relativity, both descriptions should be equivalent, but the paradox suggests that different frames yield different conclusions about the cause of the induced current. B. The role of motion in electromagnetism. The Faraday paradox points to an apparent contradiction between the relative motion of the system and the behavior of induced currents. From the perspective of special relativity, the laws of electromagnetism should be invariant across reference frames, meaning that there should be no preference for one frame over another. However, the paradox implies that in different reference frames, the induced current might appear to be driven by different mechanisms, even though the physical situation is the same. In the classical view, the current is induced because the magnetic field changes as the magnet moves. But in the frame where the magnet is stationary, the current is induced by the motion of the wire through the magnetic field. This brings into question how magnetic fields and electric fields relate to each other in different frames. 3. Resolving the paradox, the role of electromagnetic fields and relativity. A. The electromagnetic field tensor. To resolve the Faraday paradox, we need to consider the unified electromagnetic field as described by Maxwell's equations and special relativity. In relativistic physics, electric and magnetic fields are not separate entities. They are two components of a single electromagnetic field. The relationship between electric and magnetic fields in different frames of reference is encoded in the electromagnetic field tensor. The electromagnetic field tensor combines the electric and magnetic fields into a four-dimensional tensor that transforms between reference frames in a way that ensures the laws of electromagnetism remain invariant. This means that the induced current in the wire is not due to a single, simple cause, but rather the result of a combined effect of the electric and magnetic fields that transforms in different reference frames. In this framework, the Faraday paradox is not a true paradox at all. It's simply a reflection of how relativity works. The reason the current appears to be induced differently in different reference frames is that the electric and magnetic fields mix and transform as observers move between frames. While the magnetic flux through the loop changes in one frame, it's actually the underlying electromagnetic field that is transforming, and thus the observed current in the wire reflects the transformation of these fields. B. Lenz's law and the role of energy conservation. The paradox also resolves when we consider Lenz's law and energy conservation. Lenz's law dictates that the induced current will always act to oppose the change in magnetic flux. This opposition to the change in flux ensures that the energy in the system is conserved, whether the magnet is moving or the loop is moving. The fundamental law governing the induced current is still Lenz's law, which is consistent across reference frames. This conservation of energy and the inverse relationship between current and magnetic flux change removes any true paradox from the situation. 4. Real-world applications of the Faraday paradox. A. Transformers and induction. The principles underlying the Faraday paradox are essential for understanding devices that rely on electromagnetic induction, such as transformers and electric generators. These devices work based on changing magnetic fields and the induced currents that arise from them. In transformers, for example, a time-varying magnetic field induces a current in a secondary coil. The Faraday paradox illustrates the complexity of these interactions and how relative motion and electromagnetic fields govern energy transfer in such systems. B. Relativistic electromagnetism. The paradox also has implications for our understanding of relativistic electromagnetism. In high-energy systems, or when dealing with particles moving at relativistic speeds, the effects of special relativity become important. Understanding how electric and magnetic fields transform in different reference frames is crucial for designing technologies that involve high-speed particles, such as particle accelerators and magnetic confinement devices in nuclear fusion research. Two-capacitor paradox. Imagine two identical capacitors, each capable of storing a certain amount of energy. At first glance, they appear to be in equal states, same size, same material, and same charge. But here's the paradox. When these two capacitors are connected in parallel or series, their behavior might not be as straightforward as expected. The two-capacitor paradox emerges when we analyze how energy is stored in each capacitor and the potential difference between them. Depending on whether they are connected in parallel or in series, the way they store and release energy can lead to counterintuitive results. How can energy be stored differently in capacitors that seem identical? Why does connecting them in parallel or series result in different energy distributions? The paradox brings into question our understanding of energy conservation, charge distribution, and potential difference in capacitors. It challenges us to reconsider how electrical circuits behave when capacitors interact with each other. Let's dive into the two-capacitor paradox, where charge, voltage, and energy behave in ways that defy our basic assumptions about electrical systems. The two-capacitor paradox stems from the fundamental principles of electrostatics and the behavior of capacitors in electrical circuits. A capacitor is a device used to store electrical energy in an electric field, consisting of two conductive plates separated by an insulating material, dielectric. The amount of energy stored in a capacitor depends on the capacitance of the device and the voltage across it. The paradox arises when capacitors are connected either in series or parallel within a circuit. In series, the voltage across each capacitor is the same, but the charge on each capacitor can be different. In parallel, the voltage across each capacitor is the same, but the charge may differ based on the individual capacitance values. The two-capacitor paradox involves a counterintuitive outcome where, despite the same initial conditions, capacitors connected in different configurations can result in unexpected energy storage and voltage distribution. This paradox emerged in the study of electrostatics and has been discussed in the context of energy conservation and capacitive reactance. While capacitors are well understood in simple circuits, their behavior when connected in complex configurations leads to paradoxical results that challenge basic electrical engineering assumptions. The paradox continues to be a useful tool for understanding the intricacies of capacitive circuits, charge redistribution, and energy dissipation in electrical systems. The two-capacitor paradox is a fascinating concept that explores how the arrangement of capacitors in a circuit affects how energy is stored and transferred. Capacitors store energy in the form of electric potential energy in their electric fields, and the relationship between charge and voltage is governed by the equation E equals 1/2CV2, where E is the energy stored in the capacitor, C is the capacitance of the capacitor, and V is the voltage across the capacitor. The paradox arises when two capacitors, initially charged, are connected either in series or parallel. Although the capacitors are identical in terms of their capacitance, the way they store and release energy in these configurations produces counterintuitive results. Let's explore the underlying principles of the paradox and why these results occur. 1. Capacitors in series. The voltage and charge distribution. A. The basics of series connection. When two capacitors are connected in series, the total capacitance of the system is given by the reciprocal sum. 1/C_total equals 1/C1 plus 1/C2. For identical capacitors, this simplifies to C_total equals C/2. In a series configuration, the charge on each capacitor is the same. This is because, in a series circuit, the current flows through both capacitors in the same direction, meaning that the charge stored on each capacitor must be identical. However, the voltage across each capacitor will not be the same. Instead, the total voltage is divided across the two capacitors, and each capacitor will have a voltage drop depending on its capacitance. For two identical capacitors connected in series, the total voltage across the system is divided evenly between the two capacitors. Thus, the voltage across each capacitor will be V1 equals V2 equals V_total/2. B. The paradox. Energy stored in a capacitor is proportional to the square of the voltage. You might intuitively think that the energy stored in each capacitor would be the same. However, because the voltage across each capacitor is halved in a series connection, the energy stored in each capacitor is lower than you might expect based on their individual capacitance. This is because the energy is not linearly related to the voltage. It's related to the square of the voltage. The total energy stored in the system is still the same as if the capacitors were in parallel, but it's divided differently between the two capacitors. In the case of two identical capacitors, the energy stored in each capacitor will be E1 equals E2 equals 1/2CV underscore 2/2. Thus, the energy stored in each capacitor is less than expected, even though the total energy in the system remains the same. 2. Capacitors in parallel. The voltage and charge distribution. A. The basics of parallel connection. When two capacitors are connected in parallel, the voltage across both capacitors is the same, but the total charge stored in the system is the sum of the charges on the individual capacitors. The total capacitance in a parallel connection is simply the sum of the individual capacitances. C_total equals C1 plus C2. For two identical capacitors, this gives C_total equals 2C. In a parallel configuration, the voltage across each capacitor is the same. But because the capacitors have different capacitance values, the charge stored on each capacitor will be different. The charge stored each capacitor is given by Q equals CXV. Since the voltage across each capacitor is the same, the charge on each capacitor will be directly proportional to the capacitance. B. The paradox. Energy storage in parallel connection. In a parallel connection, the energy stored in each capacitor depends on both the voltage and the capacitance. Since the voltage across each capacitor is the same, but the capacitance is doubled in the total system, each capacitor stores more energy than it would in the series connection. The energy stored in each capacitor is E1 equals E2 equals 1/2CV2. Thus, each capacitor in a parallel connection stores more energy compared to the series configuration, where the voltage is split across the capacitors. However, the paradox lies in the fact that while the energy stored in each capacitor is higher in the parallel configuration, the total energy stored in the system is still governed by the total voltage and capacitance, which can lead to counterintuitive results in how the capacitors behave when charged or discharged. 3. The paradox. Energy redistribution in capacitor configurations. A. Energy conservation and redistribution. The energy paradox arises when we examine how energy is redistributed between the capacitors when they are connected in series or parallel. In both cases, the total energy stored in the system should be conserved, but the way the energy is stored in the individual capacitors can vary dramatically depending on the configuration. In the series configuration, the energy is distributed in such a way that the capacitors store less energy individually, despite the fact that the total capacitance is effectively reduced. In the parallel configuration, the energy stored in each capacitor increases because the voltage across both capacitors is the same, but the total capacitance has increased. This paradox forces us to reconsider how energy storage in electrical systems works, especially when capacitors are involved. The redistribution of energy due to the different configurations challenges our basic assumptions about how energy behaves in capacitive circuits. B. Practical implications. In real-world circuits, understanding the energy distribution between capacitors in series and parallel is crucial for designing energy storage systems, filters, and capacitive networks. The two-capacitor paradox illustrates the importance of considering both charge and voltage when designing circuits, as these two parameters interact in ways that might not be immediately intuitive. 4. Potential solutions and further questions. A. Consideration of voltage and charge. To resolve the paradox, we must carefully consider both the voltage and charge in the system. In a series configuration, while the voltage is split, the charge remains constant across each capacitor. In a parallel configuration, while the charge is split, the voltage is constant across each capacitor. The way that these factors interact in different configurations determines how the energy is distributed between the capacitors. B. The role of capacitance and circuit design. One key takeaway from the two-capacitor paradox is the importance of capacitance and circuit design in energy storage and energy dissipation. Understanding how energy is stored in capacitors and how it is redistributed based on the circuit configuration is essential for designing efficient electrical systems. A Aharonov-Bohm effect paradox. Imagine a charged particle moving in a region where both the magnetic field and electric field are zero. You would think that the particle would experience no forces and continue its motion undisturbed, yet something strange happens. The particle's quantum state changes as if it has interacted with a field, despite there being no apparent field present. This is the core of the Aharonov-Bohm effect, a profound paradox that challenges our classical understanding of electromagnetism and quantum mechanics. The paradox arises from the fact that electric and magnetic potentials, which classically represent potential energy in fields, can have physical effects on a quantum system, even in regions where the fields themselves are zero. How can a potential that we can't directly measure affect a quantum system? The Aharonov-Bohm effect reveals that the electromagnetic potentials, not just the fields, can influence the behavior of quantum particles. This paradox extends our understanding of the foundations of quantum mechanics and the role of the vacuum in determining the behavior of particles. Let's explore the Aharonov-Bohm effect paradox, where quantum mechanics and electromagnetism collide in an unexpected way, showing that the vacuum itself might not be as empty as we think. The Aharonov-Bohm effect was first proposed in 1959 by physicists Yakir Aharonov and David Bohm. They suggested a phenomenon in which charged particles could be affected by electromagnetic potentials, specifically the vector potential and the scalar potential, even in regions where the magnetic field and electric field are zero. The effect arose from the realization that in quantum mechanics, particles are described by wave functions that evolve according to the electromagnetic potentials in the system, not just the fields. The paradoxical nature of the effect became evident when Aharonov and Bohm showed that electromagnetic potentials could influence a particle's phase, leading to observable physical effects even in the absence of direct interactions with the magnetic or electric fields. This was in stark contrast to classical electrodynamics, where it was believed that fields, not potentials, were the primary agents of physical influence. In 1961, Aharonov and Bohm published their groundbreaking paper presenting the theoretical foundation of the effect. This work challenged the classical view of electromagnetism and opened new paths for understanding the fundamental nature of quantum fields. The Aharonov-Bohm effect was later experimentally confirmed in 1986 by Dietrich Volta and his colleagues, who demonstrated that electrons passing through a region with zero magnetic field but non-zero vector potential could exhibit observable phase shifts, an effect predicted by the quantum theory but completely unexpected by classical physics. The Aharonov-Bohm effect has since become one of the most important and puzzling phenomena in quantum mechanics, highlighting the deep connection between electromagnetic potentials and quantum behavior, even when fields are absent. The Aharonov-Bohm effect presents a paradox that bridges quantum mechanics and electromagnetism, revealing that the physical influence of the electromagnetic potentials, the Aharonov potential A and the scalar potential, extends beyond what classical physics would predict. While classical electromagnetism focuses on the idea that magnetic fields and electric fields directly influence the motion of charged particles, the Aharonov-Bohm effect shows that potentials themselves, even in regions where there are no magnetic or electric fields, can have a measurable effect on quantum particles. In classical physics, electric fields, E, and magnetic fields, B, are the primary agents that affect the motion of charged particles. These fields are typically described by Maxwell's equations, which relate the behavior of fields to the sources of charge and current. The force on a charged particle in an electromagnetic field is described by the Lorentz force law. F equals Q E plus Vx_b, where F is the force on a charged particle, Q is the charge of the particle, V is the velocity of the particle, E is the electric field, and B is the magnetic field. In classical theory, the electric and magnetic fields directly influence the particle's motion through the force they exert. However, there are also associated potentials, the electric potential and the vector potential A, from which the fields can be derived. E equals max A. In classical electromagnetism, the fields themselves, E and B, are the quantities that directly affect a charged particle. The potentials and A are used as mathematical tools to calculate the fields, but they are not seen as directly influencing the motion of particles. The idea was that only the fields, not the potentials, had observable physical effects. In classical electromagnetism, the potentials were considered auxiliary variables, Useful for solving problems but not physically significant on their own, the electric field and the magnetic field were considered the real agents of influence. The potentials were regarded as a convenient but non-essential part of the mathematical description of the system. However, the Aharonov-Bohm effect upends this classical view by showing that the potentials themselves can have physical consequences, even in regions where the fields are zero. In quantum mechanics, particles like electrons are described by wave functions that evolve over time according to the Schrödinger equation. The wave function carries information about the probability amplitude of the particle's position and other properties. A key aspect of quantum mechanics is the superposition principle, where particles exist in a superposition of states until they are measured. The quantum mechanical description of a charged particle in an electromagnetic field involves in the electromagnetic potentials A and M, rather than directly using the fields. In the minimal coupling prescription, the vector potential A and the scalar potential enter into the quantum Hamiltonian, influencing the particle's wave function. H equals 1/2 mppqa 2 plus q, where h is the Hamiltonian energy operator, m is the mass of the particle, p is the momentum of the particle, q is the charge of the particle, a is the vector potential, and is the scalar potential. This formalism shows that the potentials themselves play a key role in determining the phase of the particle's wave function, even in regions where the fields E and B are zero. To understand the Aharonov-Bohm effect, consider a situation where a charged particle moves along two different paths that encircle a magnetic flux. In the region between the two paths, there is no magnetic field, but the vector potential A is non-venom due to the presence of a solenoid, a magnetic field confined to the solenoid's core. The particle's wave function picks up a phase shift as it moves along the two paths, depending on the amount of magnetic flux enclosed by the paths. The key result is that the interference pattern, which can be observed by measuring the probability distribution of the particle, depends on the magnetic flux through the solenoid, even though the particle never actually enters the region with a non-zero magnetic field. This indicates that the vector potential A has a physical effect on the particle, despite the absence of a field. The Aharonov-Bohm effect leads to the paradoxical conclusion that electromagnetic potentials have physical significance and can affect the behavior of a quantum system, even in regions where the fields themselves are zero. This is in direct contrast to classical electrodynamics, where fields, not potentials, are seen as the primary agents of interaction. The paradox arises from the fact that while we are used to thinking of magnetic and electric fields as the agents that affect particles, the Aharonov-Bohm effect shows that potentials themselves, through their influence on the wave function, are also capable of producing observable effects. The key question is, how can something that appears to be a mere mathematical tool, like the vector potential A, lead to a measurable physical outcome? In 1986, the Aharonov-Bohm effect was experimentally verified by Dietrich Volta and his colleagues. They set up an experiment in which electrons were passed through a two-slit setup surrounding a solenoid carrying a magnetic field. The result was a clear phase shift in the interference pattern, proving that the vector potential A influences the electron's wave function, even though the magnetic field was confined to the solenoid. This experimental confirmation solidified the Aharonov-Bohm effect as a cornerstone in the study of quantum mechanics and electromagnetic theory. It demonstrated that potentials, not just fields, play an active role in shaping the behavior of quantum systems.